Hello everyone, and welcome to our third RTC at Scale conference. It's great to be here with you all. I'm coming to you from Meta's office in Menlo Park, California. My name is Lital Mashiach, and I have been with Meta for 12 years. Since 2016, I have been the engineering lead for real-time communication, where we develop the calling features for Meta apps, including Facebook, Messenger, Instagram, WhatsApp, and new products coming from Reality Labs. I love how RTC is connected to Meta's mission of bringing the world closer together, and I'm proud to be one of the organizers and your host for today's conference. Our first RTC at Scale conference was 2 years ago. During the pandemic, I remember hosting this conference from my home. Back then, the usage of audio and video calls exploded. Then last year, we saw some evidence that the boost in digital communication is here to stay also post-pandemic. And this year, I'm excited to share that the increase in usage continues to drive a lot of developments and innovation across the industry. We are going to have with us today technical leaders, entrepreneurs, WebRTC experts, and leads from Meta, Intel, Visionular, and LiveKit. We've structured our discussions across 3 session blocks. This format will give us a full view of the recent developments and innovations. To kick off our event, we will open with a keynote about broader RTC trends and how Meta products connect users, delivered by industry leader Nitin Khandelwal. We'll then begin our first session block, Real-Time Quality at Planet Scale, on how Meta revamped audio quality and Meta's strategies to improve quality for international calls. Then we'll go into our second session block on next generation of real-time video. Here we will explore the recent innovation to redefine the way we experience video connectivity, offering a glimpse into what the future holds for digital interactions. We will end the day with a final session called RTC, the Not So Obvious. In this session, we will talk about things in real-time communication that people don't usually think about, including some expert analysis and exciting ML work. We will discuss how these hidden and unexpected things are changing the field in big ways. Each session block will be followed with a live Q&A session with the speakers, so please share your questions at our AtScale conference websites, live stream, in the chat box. All presentation, live Q&A sessions, and blogs will be posted to the AtScale conference website, as well as at the AtScale social pages following the event. So in case you miss something, you don't need to worry. You will be able to access all of the content after the event. Thank you for being here today. If you have any questions or ideas for future AtScale events or Meta Tech blogs, you can visit our website at atscaleconference.com or scan the QR code on the screen. Now, it is my pleasure to introduce our keynote, From Codec to Connection. Our keynote speaker is Nitin Khandelwal. He is Director of Engineering at WhatsApp. Here in Meta, Nitin is leading strategic innovation in the digital communication field. Before his role at Meta, Nitin was a Senior Director of Engineering in Google, contributing significantly to products like YouTube Search and Google Assistant. His expertise in leveraging data-driven insight and machine learning has dramatically enhanced user engagement with these products. Nitin has a long history as an innovative leader that drives improvements in global user experiences. Please join me in welcoming Nitin.
Hello everyone. Glass, titanium, and silicon make up our primary method for connecting with each other. Our principal means of contact is not physical. My family is in India, and most of our hugs and conversations are virtual. We are not present physically together, yet technology like RTC is creating presence. At Meta, our purpose is to be an enabler of human connection. We look to build ways for people to be ever present, coming together in unique ways through technology. Across a wide range of media, text, audio, video, live chat, we are changing the definition of presence, even bringing the richest experiences in the metaverse with the advances we are making in RTC. We enable vibrant global communities to discover new things, connect with each other, and open their world in big and small ways. My dad and I live across the world, but we are connected through Meta. Here is what a day might look like with my dad. I send him a message with a video of his grandson Arjun, who is 6, telling him all about ziplining for the first time. He was very excited about being brave because it was so high to him. My dad responds with a live chat and we message about what has been going on. He wants to know Arjun's favorite part and how he wants to learn to zipline too. We have a live conversation with a call and share pictures of Arjun doing it. Arjun tells him all about how at the end he got to splash into a pond and swim to the side. My dad tells him how proud he is. Even though we are far away from each other, I am able to build a bond between my dad and Arjun that wouldn't happen otherwise. He and Arjun have an incredible relationship, despite the fact that we don't live near each other. When I think about presence and connection, it's about understanding and delivering on two prevailing needs that people have in building meaningful relationships. Always possible to connect and to be fully present. Real-time calling is crucial in delivering on these needs. People have the need that it is always possible to connect. They look to have the convenience and ability to use any device on any network. They will have a seamless, private, and a high quality way. People also have the expectation to be fully present. Users look for rich experiences that can be started instantly. We need to enable people's ability to connect with each other across a wide range of modalities and platforms. And we need to support them anytime, everywhere, whether it's a one-on-one connection or a large group moment like a surprise celebration for a birthday or important conversation with the work team. Our users' primary needs are always present in how we think about the experiences that we serve in Meta products. At Meta, our investment in real-time calling plays an important role in our goal to bring people together when they are apart. The first experience is daily calling. Connecting with close contacts is the majority of the calling people do. We provide a simple, secure, and reliable way, available on devices all across the world. This is increasingly driven by the advancements in AI. We improve access to daily calling by optimizing for low-end network conditions. We developed a new codec that delivers high-quality audio while using lesser bits as compared to the industry standards. To further enhance audio clarity, we have two modes of acoustic echo cancellation: a light mode for low compute devices and a full mode which delivers high fidelity stereo on higher compute devices. By using the Meta backbone with novel multi-hop solutions, we ensure packets are delivered reliably and with low latency, whether it's across the street or across the ocean. And this allows people, including my dad, sisters, and I, to connect across the globe. We are extending into a wider range of form factors in creating unique experiences. One example is the Ray-Ban Meta Smart Glasses. I can show you the world as I see it. Or in this case, I can feel like I'm on stage with Maluma. It creates a sense of togetherness in a more natural and fun way. The next core experience we consider is collaboration, which includes communicating with work contacts, engaging in communities, or travel planning. This might entail connecting a large group of people to organize an event or sharing pictures and browsing accommodation options when planning for a trip. To facilitate better group collaboration, we have developed specific features such as joining ongoing group calls at any time. This provides a flexibility for calls with a large number of participants. And since these calls often last longer, people prefer to use their desktop or tablet instead of a mobile phone. We understand this and make sure our tools are convenient to use on all device types. We bring in new technology solutions like codec avatars into the product experiences like Meta Horizon workrooms. We connect distributed and hybrid workers in seamless ways using tools like VC bridges and screen sharing content. Horizon and the Meta Quest mixed reality headsets make it possible to build communities, run immersive events, and collaborate effectively in the meetings. Kodak Avatars represents a groundbreaking innovation in the realm of mixed reality. They're hyper-realistic representations of users, designed to mirror their real-life appearance and expressions with astonishing accuracy. To make this experience come to life requires a wide range of RTC enhancements. For example, to capture and render the environment with high fidelity, including people's facial expressions and spatial audio, or efficient multi-channel compression and transmission for a realistic representation. This is how workrooms will build a seamless experience in a natural way. We know there are several key elements to a social strategy, including the metaverse. At a high level, we want people to more easily connect in the moments. Our goal is to enable people to connect in real time, no matter what the size of the group is, for casual hangouts and interactions, fostering discussions, and creating shared experiences. Now, friends and groups are able to easily engage without the need for a formal call. People either used group calling or group messaging because there was not a way for them to work together. Now they're complementary with voice chat, which enriches group chats because you can easily incorporate real-time communication to the conversation. For instance, I have a chat group with several former colleagues. It's a lunch club, and we are all soccer fans. When a goal is scored during a soccer games, we can instantly hop on a voice chat with those watching the game, and without ringing the entire group. I use this quite often to brag about Messi's goals. The seamless combination of messaging and voice enriches our conversations and allow us to share moments and celebrate together. We have the potential for much richer human connection through our Horizon experiences. For example, mixed reality pass-through capabilities on MetaQuest allows us to create co-located games you can play with friends in the same physical room, or productivity experiences that combine huge virtual monitors with physical tools. We are able to push the boundaries of what is possible in a social interaction. But technology is so realistic that it disappears into the background, pushing the social aspects to the foreground. High fidelity real time communication is the key to fulfilling the metaverse promise of identity expression and social presence. We have a responsibility to be a good steward in the industry. That means to me, interoperability standards are an absolute requirement. We will need to be mindful that we need to build and share standards so that we can serve everyone. I also want to reiterate Meta's commitment to build an open source general infrastructure while keeping a specific product implementations proprietary. This approach to open source is already unlocking a lot of innovation across the industry, and it is something that we believe in deeply. Also, at scale series is yet another way where it all comes together to rally beyond in RTC to solve hard problems together at scale. I think a lot about what and where I will be in 10 to 20 years with my own son Arjun, how we will be present in each other's lives, and how technology will be key in our relationship. I imagine the potential that Arjun could be hiking somewhere I've never been, and he's taking me with him. I can experience the world as he sees it. I'm experiencing it through a metaverse environment. I can be present with him in those once in a lifetime meaningful moments. I'm excited to see where we can take real time calling in our work together. This conference is one of the opportunities we have to explore how we can continue to make the ways people can connect much stronger. I encourage everyone to get involved and be a part of conversations happening at the conference. Thank you.
Thank you, Nitin. We'll begin our first session block with a two-part series on revamping audio quality for RTC, where we dive deep into some groundbreaking work to reshape how billions of users across WhatsApp, Instagram, and Messenger experience audio calls. In the first part of the audio talk, Barrel echo cancellation, Sriram Srinivasan and Hong Do will be taking us through the challenges of tackling one of the most common yet annoying issues in real-time communication, echo. You know, that weird experience of hearing your voice coming back at you during a call? They've been working on some cutting-edge solutions to make that a thing of the past, ensuring clearer, more natural conversations no matter where you are or what device you are using. We'll then move directly to part 2, Mllo, audio codec, where Jatin Kumar and Bikash Agarwala will share the details about new audio codec specifically designed for low bandwidth scenarios to ensure high quality audio to all users, even in low network conditions. They are also excited to share the recent launches that make calling across our family of apps a smoother and more enjoyable experience. Please welcome Sriram Srinivasan, Meta's lead for real-time audio teams and one of my partners in organizing today's event. With over 15 years of experience in advancing audio technology across apps like WhatsApp, Instagram, and Messenger. Take it away, Sriram.
Welcome to the audio session at this year's RTC at Scale. My name is Sriram Srinivasan, and I'm joining you from our Seattle area office, where I lead engineering teams spread across various locations who work on audio technologies for real-time calling at Meta. WhatsApp is a regular part of my life. It's how I stay connected to my extended family around the world. It's how my kids stay in touch with their grandparents and cousins, just like billions of other people who use one of our apps, Instagram, Messenger, Facebook, and WhatsApp, to stay connected with their loved ones. It's a privilege to be able to come into work every day and improve the calling experience for our users. We worked very hard on revamping the core of our audio processing stack to deliver a great audio experience across all devices and networks. And I'm excited to share more details with you today. My colleagues Hong, Jatin, and Bikash will join me in a bit as we cover how we did this and the impact on our users. But first, let me start with some context on why we did this and how it fits into the real-time audio pipeline. Let's start with a look at the mouth-to-ear real-time audio chain, starting with audio capture, enhancement, encoding, packetization, and transmission over the wire, packet loss and jitter compensation, decoding, post-decode enhancement, and rendering. Last year, I spoke about how we addressed a no audio or the device reliability problem at Meta, focusing on the first and the last blocks in this diagram, low latency, reliable audio through efficient capture and render device management. Since then, we've continued to make great progress, including a 20% reduction in no audio problems across both iOS and Android last year, and a 15% reduction in the P50 mouth-to-ear latency on Android. Today, I'm excited to talk about how we revamped the core of our audio processing stack at Meta, powering calling across WhatsApp, Instagram, and Messenger. Barrel, our new echo removal solution, and Mllo, our new low bitrate audio codec. This is the result of our long-term investments and innovation in this area. Our apps are used by billions of people around the world for voice and video calls, and for a variety of use cases. Our user base is very diverse, making calls using a wide variety of devices, both high-end and low-end phones. Users connect in different network conditions, on the go, under background noisy conditions, and our goal is to leave no user behind. Providing consistently great audio quality is important regardless of the user's device or network. Based on our telemetry and user feedback, we decided to tackle two key problems: echo and audio quality under low bitrate network conditions. There's a lot of excitement around AI-based echo removal and codecs, and at Meta, we realized the value of ML early. On devices that can afford higher computational complexity, we've launched a machine learning-based approach that suppresses echo, preserves double talk, and also suppresses various types of background noise. At the same time, we need a baseline solution with wide reach that is lightweight in terms of CPU and memory, and yet provides a significantly better quality than our current state-of-the-art solution, even on the lowest end of our devices. This is where Barrel excels, replacing WebRTC's AEC3 and AEC-M on our apps across all of our users' devices. Similarly, we have AI-based neural codecs at Meta that offer excellent quality at low bit rates. For the RTC use case, however, often the users who experience the low bitrate conditions are also on the lowest end of our devices. More than 20% of our calling users across apps are on ARM v7 low-end devices. This demands a low CPU solution. In today's talk, we'll start with echo first and then move on to the new audio codec. Before diving into AEC or acoustic echo cancellation, let's define the problem first. Let's look at a call between Alice and Bob. Alice's voice, captured by the microphone on her side, is processed and sent over the network, played out of Bob's loudspeakers. Bob's microphone captures his own voice along with Alice's voice that is then played out of his loudspeakers. If Bob's device does not have an effective AEC to cancel out Alice's voice, both of the voices would be sent back to Alice. Alice would then hear her own voice. We call this acoustic echo. Echo is disruptive in both one-on-one and group calls. Having a good AEC is crucial to a natural communication experience. Some calling apps leverage the built-in hardware AEC provided by the device. Others implement their own software AEC. But at our scale, we found that for a large number of devices, hardware AEC is either not present or is ineffective. Also, many advanced calling features such as stereo or spatial audio are only possible when using software echo cancelers. Many hardware AECs operate in mono mode, and therefore, we chose to invest in this important problem of building a good software AEC. I'd like to invite my colleague Hoang Do to walk us through how we built Barrel, our new software AEC. Hoang Do leads the remote presence audio algorithms team at Meta, working on audio DSP and ML technologies for real-time communication. Prior to Meta, he was at Amazon, where he helped build the Amazon Chime SDK. He holds a PhD in audio signal processing and has over 10 years of experience in building audio products and services in both startups and large corporations. I'm incredibly lucky to have Hoang in my team, and I'm delighted to hand it over to him to talk about Barrel.
Thank you, Sriram, for the introduction. Hi, everyone. I'm Hoang Do, software engineer at Meta. And today, I will talk about our latest in-house Barrel AEC on both the algorithm and real-time implementation fronts. At the end, we will also listen to a demo of Barrel AEC versus WebRTC AEC-M from messenger calls on real Android phones. The WebRTC AEC-M, short for AEC Mobile, and AEC3 are the two widely used software AEC solutions in the RTC space. AEC-M is essentially a low-compute echo suppressor that is meant to be used on mobile platforms. AEC3, on the other hand, is a full-fledged AEC that is suitable for more compute-capable platforms like Mac or Windows desktops. These open-source solutions provided by WebRTC have powered the growth of real-time communication. We would not be able to get to where we are today without the WebRTC Foundation. However, there are two unique challenges to meta-RTC use cases where the WebRTC AC solutions fell short. First is scalability, and second is quality. On the scalability front, our applications need to work well for millions of devices in different acoustic conditions. On the quality front, AEC performance is sensitive to many factors, such as the audio level, the acoustic coupling between the speaker and the microphone, any nonlinearity introduced in the acoustic paths between the two devices, either by the hardware, for example, A2D or D2A converters, or software, for example, dynamics processing like compressors or limiters, or the time delay between the far-end reference and the near-end capture signals. It became necessary that we needed to build our own software AEC solution that is robust to both the scalability and quality challenges. Enter Barrel AEC, our in-house low-compute DSP-based software AEC solution. In the next slide, we will have a quick high-level overview of Barrel AEC. We designed Barrel AEC algorithm as the baseline, scalable DSP-based AEC solution for all of our users. That is why Barrel AEC comes in two modes: light mode, suitable for low-compute devices like low-end phones, and full mode, which is suitable for more compute-capable devices like high-end phones or desktops. Both are adaptive AEC as opposed to AECM being a simple echo suppressor, with near-instant adaptation to room impulse responses changes or volume changes, and provide a better double talk performance. Both modes support multiple capture and render channels, which is essential for applications like high-fidelity stereo audio or spatial audio. And they can work with either 16 or 48 kHz sample rates. They are also tuned by using a comprehensive dataset with more than 3,000 clips of music and speech in both mono and stereo formats, recorded on more than 20 real devices in different acoustic conditions. Both are relatively low cost in terms of CPU, with less than 7% increase from their WebRTC counterparts. Next, we will dive deeper into the three main components of the Barrel algorithm itself. The first component is the delay estimator. Have you ever wondered why you might hear some echo leak in a call with an audio setup using external microphone and speaker? This setup could result in some clock drift over time, as the two devices run on two different clocks. And if the delay estimator is not robust enough, it would result in echo leaks. The job of the delay estimator is to estimate the time delay between the far-end reference signal, which is the signal that gets played out by the speaker, and the near-end capture signal, which is the signal that gets captured by the microphone. In theory, this delay corresponds to the time it takes for the sound wave to leave the speaker, travel through the air, and reach the microphone. However, in practice, there might be other sources of delay, such as internal audio buffers get held up in the case of loopback on the desktops, or thread jitter due to OS scheduler, or clock drift if the speaker and microphone operates on different clocks. A good delay estimate is crucial to the success of the AEC, as the AEC adaptive filters often employ limited tail length to reduce the computational cost, and therefore cannot capture too long or non-causal negative delays. Barrel full mode can handle non-causal delays, which could happen if the loopback signal on desktops get delayed. On the other hand, Barrel light mode, which targets mobile devices, is only concerned with non-negative delays. The range of the delay supported by the delay estimator is also configurable. It can be up to 1 second for some extreme cases like virtual audio drivers with network latency. The second component of Barrel algorithms is the linear AEC. This is the heart of an AEC algorithm and where the magic happens. After the reference and capture signals are aligned by the delay estimator, the job of the linear AEC filter is to estimate the echo present in the capture signal and subtract it from the signal to provide a close estimate of only the near-end audio without any echo in it. In essence, the linear adaptive filter does this by iteratively estimating the acoustic paths between the speaker and the microphone, also known as the room's impulse response, generating the echo estimate from this and subtracting it from the input signal to derive the output, also known as the error signal. Barrel linear AEC is a normalized least mean square or NLMS frequency domain dual filter algorithm. It consists of a fixed filter and an adaptive filter, where the fixed filter does not adapt, which helps the AEC during steady state, and the adaptive one always adapts, which helps the AEC converge quickly to changes. During operation, the coefficients of the two filters in each frequency band can be copied in either direction depending on some criteria. For example, the relative difference in the powers of the error signals between the two filters and the input microphone signal, or the coupling factor between the echo estimate and the error signal. The adaptation step size is also variable, depending on the coherence between the microphone and reference signals, as well as other factors like the power and signal-to-noise ratio of the signal. This design of the adaptive filters allows a superior double talk performance compared to that of the WebRTC ones. The third component of Barrel algorithm is the acoustic echo suppressor, or AES. In the propagation path from the far end to the near end, there might be some nonlinear distortions, such as those introduced by the amplifiers before the speaker and after the microphone. The linear AEC can only remove the linear part of the distortion, and it is the job of the AES to remove the nonlinear echo, also known as residual echo, left over from the linear AEC processing. Barrel AES removes stationary echo noise, applies perceptual filtering, and ambient noise, matching, in both level and color, to effectively remove the residual echo and preserve the nature of the speech, as opposed to WebRTC AES, which does not offer these features. As a result, WebRTC AES outputs often has gated, jarring bursts of echo and comfort noise. Next, we will discuss some best practices and learnings when implementing Barrel AEC in a real-time system. In order to make Barrel AEC work well as a baseline solution across all devices, including low-end devices, it was necessary to reduce its memory, CPU, and latency footprints. This is not an easy task and requires some careful engineer implementation. In this section, we will discuss some best practices and learnings as we brought Barrel AEC algorithm to life in production. First, thread safety. An AEC consumes the two signals, the near-end capture signal and the far-end reference signal, provided by two system audio codecs running on the input and output real-time audio threads, respectively. Since the read and write operations of such data can happen simultaneously from the two audio threads, care must be taken in order to avoid race conditions. To ensure that the read and write of the common data structures is thread safe, different techniques can be used. First, apply a high-level lock like mutex on the function level. Such as functions to write to and read from the capture and render buffers. This approach has the lowest risk in terms of breaching data integrity and running into race condition, with the trade-off of having the worst real-time performance, because one thread is blocked while the other is holding the mutex and processing. Second is to apply low-level locks on only the data structures that can be concurrently mutated by different threads. This approach has the medium risk with the relatively good real-time performance. And third is to use lock-free thread-safe data structures to store the data that might be mutated concurrently. This imposes the highest risk, since all the data can be valid on their own, but the combination might not be. However, this approach has the best real-time performance without any blocking. Implementers can decide which approach to use depending on their real-time performance requirements and risk tolerance. Besides thread safety, real-time AEC systems also need to consider CPU and system side information. Letting the AEC know about the side information such as audio device route changes, mute-unmute events, volume changes can help it take appropriate actions. For example, to reset the internal states to make the convergence of the adaptive filters happen faster. To optimize for CPU, we write Neon code for most of our DSP functions that can be run on either ARM64 and ARMv7 CPUs for mobile platforms. We also utilize AVX2 optimization on devices using Intel CPUs. And as a result, despite being a full-fledged AEC, Barrel CPU is no more than 10% higher than that of the WebRTC AEC counterparts, with significantly better quality, as we will see in the next slide. In this slide, we show two short recordings from live calls on Messenger for Android. First, using WebRTC AECM, and second, Barrel AEC on two real phones, both without hardware AEC. One can hear that Barrel AEC output does not have the residual echo and noise like that of the AECM. While using WebRTC's AEC, you can hear the occasional echo or a distorted version of it.
This can be annoying and add fatigue in longer calls.
While using the new Barrel AEC, you will notice that there is no echo or distortion.
This is a much better experience.
Next, I will hand over to my colleague Sriram to talk about the performance results of Barrel AEC in both offline and online production settings.
Thank you, Hong. That was a great overview of the complexities involved in addressing the echo problem, as well as the deep work that went into researching, developing, experimenting, and shipping Barrel. We evaluated Barrel AEC performance using subjective listening tests, as well as objective technical metrics from production calls. In our subjective listening tests, we evaluated both Barrel AEC and WebRTC AECs using ITU P.831 standards on a dataset with over 1,000 audio samples constructed from both real recordings and synthetic data on different devices, acoustic conditions, sample rates, and content. These tests evaluate the impact of the various algorithms on two dimensions, echo annoyance and double talk. Both Barrel Lite and Barrel Full are significantly better than their WebRTC counterparts. The first dimension in these subjective tests is echo annoyance during single talk. This is when Bob is silent, Alice is speaking, and Alice should not hear herself back. Barrel Full is 37% better than AEC3, and Barrel Lite is 26% better than AECM. Echo annoyance during double talk. Here, both Bob and Alice are speaking. Alice or Bob should not hear themselves back. Barrel Full and Barrel Lite are 39 and 29% better than their respective WebRTC counterparts for this scenario. Near-end quality during double talk. This one is challenging. Both Bob and Alice are speaking. We expect Bob's voice to come across clearly to Alice and the other way around, but without echo. Here, Barrel Full and Barrel Lite are 14 and 38% better than their WebRTC counterparts. Notice the significant improvement Barrel Lite has for our mobile users. We also compared the performance of the two AECs using our technical metrics collected from calls in production. On both Instagram and Messenger Android, Barrel AEC performs better than WebRTC AECM, and we observed statistically significant improvements in talk time, in thumbs down ratio, which is a measure of user satisfaction that we collect at the end of our calls, user reports of echo, and other technical metrics. That brings us to the second talk in the audio session. Delivering high-quality audio using as few bits as possible has been an interesting challenge for the industry. I'd like to invite Jatin Kumar and Bikash Agarwala to walk us through how we solved that problem at Meta with Mllo, Meta's new low bitrate audio codec. I worked closely with Jatin and Bikash for the last 2 years, and I'm incredibly proud of this work. Providing full-band audio at bit rates as low as 4.2 kilobits per second and roughly the same computational complexity or even a little bit lower than Opus. Jatin Kumar is a software engineer and tech lead for WhatsApp's calling audio team at Meta, where he has significantly improved audio quality for billions of users over the last 3 years. Prior to WhatsApp, Jatin spent 3 years scaling the core RPC routing library to millions of servers at Meta and improving its reliability. Jatin's leadership and technical expertise have been crucial in enhancing global communication through WhatsApp, showcasing his commitment to innovation and excellence in the tech industry. Bikash Agarwala is an engineering manager at WhatsApp working on calling products for more than 4 years. He has 15 plus years of experience building and growing various monetization and consumer products at Meta, such as calling, payments, donations, fundraisers, and more. He's motivated by the large impact his work has on a massive user base and focuses on key areas of RTC, such as audio and video processing and packet loss recovery. He holds a PhD in computer science from Georgia Tech. Over to you, Bikash.
Thanks for the introduction, Sriram. We learned so much about how Meta removes echo and noise from your talk. The next important part of the audio pipeline is the encoder. We all know that raw audio content is large, like hundreds of kbps, so compression is must. Codecs are used to compress the audio payload before they are transmitted to the other side. Similarly, a decoder is used to convert compressed audio back into the audio signal. The audio codec tries to balance various competing parameters such as complexity, quality, latency, battery consumptions, etc. As an example, An audio codec may be able to provide great quality audio with good compression, but may be computationally too expensive. That may make it not usable for real-time communication use case. An ideal codec keeps the quality good while keeping complexity manageable. You may still wonder why we need a new codec. A lot of our users are still using low-end devices. For example, 2% of daily calls on WhatsApp are on 10-plus-year-old devices. In the future, we also want to serve the population that may be coming to the internet for the first time on low-end phones and on low-end market. There are multiple codecs out there, but they don't fit our unique requirement. For example, Opus is a 11-plus-year-old codec that is currently used in production across our family of apps. While it met our basic needs, we are seeing evidence that users are struggling with audio quality in calls on low-end network and devices. Audio breaks, audio delays are some of our top reported user complaints for audio quality. Lyra and Lyra 2 from Google are ML-based low bitrate codec. They are high on complexity, 5 to 7 times more complex than Opus in encoding. There are other AI-based codec, including at Meta, which are well suited for streaming music but not for voice calls. Therefore, we want to innovate in the codec technology by building the first audio codec that supports really low bitrate but without the added complexity in binary size or computation. So for the new codec, we started with few requirements. Number 1, full band 48 kHz audio quality starting at 4.2 kbps and scaling to higher bitrate. Number 2, light enough so that it runs on all devices that our users are on to support Meta's diverse user base. Computational complexity not greater than that of Opus complexity at mode 5. Flexible and extensible to support use cases such as flexible FEC, spatial audio, group call, etc. And easier to integrate with reusing codec API as much as possible. We put extra emphasis on keeping complexity in check. This is based on the fact that we can come across many great sounding ultra low bitrate codecs, but unfortunately they don't work on end user devices due to often being very highly complex. For example, from experiments we know that a complexity increase by 90% has led to engagement drop of 0.3% and connection drop of 0.75%. Therefore, it is really critical to keep the complexity low while we optimize for quality. In practice, this meant using ML very judiciously without increasing complexity and doing a lot of optimizations using traditional DSP techniques. Now I will hand it off to Jatin to talk more about the codec development.
Thanks Bikash for answering why we need a new codec. Let's get to how we built it now. At the heart, Mllo is a traditional calc-based codec which uses linear predictive coding, aka LPC, to model the incoming speech signal. In the encoding process, it searches for the optimal model parameter such that the synthesized signal generated by the decoder will have minimum error. As a result, you can think the encoder internally runs parts of the decoder multiple times to find the best match. This is what usually makes a kelp encoder expensive than the decoder. This technique is not new, and there is tons of public domain knowledge available on this. While using kelp allowed us to keep complexity in check from the beginning, our innovations around excitation coding, novel quantization methods, and coding schemes allowed us to achieve high quality using very low bit rates. Digging into the high-level codec design, we split the incoming signal into 2 frequency bands and treat them separately. It is worth noting that most of the speech content is in the low frequency band like 0 to 4 kHz, and the higher frequencies are used to enrich the signal and provide a more natural sounding experience. So naturally, we spend more bits in encoding the low frequency bands as compared to the high band. With novel ideas and by sharing information between the low and the high bands, we are able to encode high band with less than 1 kilobit per second of overhead. This allows us to encode super wideband and full band content at very low bit rates. All the output from the 2 encoders is entropy coded into single bit stream and then sent out to the other side. On the decoder, we pretty much reverse the whole process. It starts by separating out the low and the high end signals from the encoded bit stream, then decodes them separately and then combines them to get the desired output audio signal. Designing a new codec from scratch is a really hard engineering problem. While the design looks simple, there are tons of details intentionally left out to keep it consumable for this talk. Next, let's look into how we were able to develop and iterate so fast. Developing a new codec requires a lot of experimental and throwaway work while trying out many different ideas. Although the final codec would have been in C or C++, we chose to do initial prototyping in Julia language. Think of Julia as a powerful combination of MATLAB and Python with an amazing collection of DSP libraries. It allows writing expressive code through first-class support for vector operations. Once we had a working prototype in Julia and it met our quality requirements, we started with Julia to C conversion. As we converted the modules one by one to C, we were able to call the C code from Julia and made sure everything continues to work well. Although Julia has a fast runtime, but it was only in C or C++ codebase that we were able to get a true assessment of the codec complexity. As expected, it required us a few iterations to bring down the codec complexity to meet the low complexity bar we had set for ourselves. All of this while keeping the high quality. We had kept the Julia and the C implementations in sync, which again allowed us to quickly try out a few ideas to meet complexity requirements. Now that we had a working prototype, we were able to evaluate the codec and assess its quality. Codec development often requires using a large dataset of diverse audio content, so we are able to correctly capture the sound characteristics of different languages, gender, and surrounding environment. In some ways, it is similar to training a machine learning model, and you don't want to overfit a certain segment of users. Given Meta's global scale, we had to ensure that the codec works for everyone in every scenario. So we used thousands of audio files distributed across various languages like English, Spanish, Italian, etc., with good representation of male, female, and children voices. These languages represented Meta's user distribution. We synthesized and mixed various stationary and non-stationary noises with clean speech signal to represent users talking in moving cars, supermarkets, and other noisy environments. Lastly, to test certain codec features like packet loss concealment, we synthesized different types of lossy network conditions. While we were able to find good public datasets on wideband clean speech, there is not much speech content available with finer details like super wideband or full band. Meta ran a standalone program to collect full band speech content where users read out phrases, and this allowed us to evaluate and test the codec for higher frequency content as well. We have collected an exhaustive data set and generated audio files with the new codec now. But how do we compare the quality of one codec with another? Let's see how we evaluate it. Perceptual audio quality is a very subjective metric, and everyone perceives it differently based on their attention for details, age, and surrounding environment. There are some objective audio evaluation tools like Whisker and Polka, but you cannot rely on them 100% as these tools are not perfect. We adopted ITU standard P808 to perform crowdsourced listening tests and get mean opinion score to rate audio quality on a scale of 1 to 5, with 1 being very poor to 5 being excellent. These tests required finding listeners in various languages, evaluating same file across multiple listeners to remove any listener bias, and doing so across thousands of evaluation files. We were able to establish a high confidence in the process with the repeatable results across multiple runs. These tests are highly time consuming and often require multiple weeks of turnaround time, and so these cannot be used very frequently. For everyday development, we relied on testing using a handful of audio files with manual listening and had an automated setup which ran objective tools like Whisker Polka on each commit to provide a wider safety net across a large dataset. After nearly 1.5 years of active development, we were able to finish the codec development and evaluation and ready to bring it to life. No codec talk is complete without a real demo. Please listen to the demo for yourself and compare how amazing the new codec sounds. We suggest that you use your favorite pair of headphones to truly appreciate the quality differences. This codec has original speech content, followed by Opus running at 6 kbps, then Mllo running at just 4.2 kbps. Let's play the demo.
We, the people of the United States, in order to form a more perfect union, establish justice, ensure domestic tranquility, provide for the common defense, promote the general welfare, and secure the blessings of liberty to ourselves and our posterity, do ordain and establish this Constitution for the United States of America. We, the people of the United States, in order to form a more perfect union, establish justice, ensure domestic tranquility, provide for the common defense, promote.
I hope you were able to tell that Mllo sounded much more crisp than Opus because we were able to capture higher frequency content as well on lower bit rates. What makes it really special is that Mllo is able to achieve this using 10% less compute than Opus. This is very significant improvement as compared to most ML AI codecs, which are 5 to 7x more complex than Opus. While you have heard the amazing quality yourself, let's see what the crowdsourced listening tests have to say. We evaluated Mllo at various bit rates against Opus, and here are the key highlights of our final round of evaluation. Mllo at 4.2 kbps is 1 plus most score better than Opus at 6 kbps, while using only 90% of Opus compute. This equates to roughly 110% better quality than Opus at these lower bit rates. Mllo saturates quality faster than Opus. As a result, Mllo at 18 kbps is similar or better than Opus at 25 kbps. Even with objective evaluation tools like Polka, we are able to roughly capture the quality difference as you can see with the graph on the right. Mllo is much better than Opus on the lowest bit rates where we innovated the most, and the gap closes down at higher bit rates. We were very happy with the offline evaluation results, and thanks to the strict complexity criteria, we were confident in getting it out into the hands of our users quickly. Let's learn more about our production testing from Vikash.
Thank you, Jatin. I'm happy to share our results from getting this new codec in our production apps. Opus has been the main codec for our family of apps and has been optimized heavily over the years. As you can imagine, replacing such core piece of technology with better quality is really hard. We performed extensive A/B testing in production, comparing Opus against Mllo, and we are excited to share that as of today, we have launched our Mllo codec for all calls on Instagram and Messenger and a major part of WhatsApp calls. In addition to audio quality improvements, Mllo also allows us to improve video quality. By lowering audio bitrate without compromising quality, we can give more bits to video, therefore improving video quality. We saw significant user engagement gains, call survey rating improvement for each of our launches. We started in this journey 2 years ago to build new audio technology that provide great quality for our users. We are excited about the results we were able to achieve with Mllo and are actively working on getting it in the hands of more and more users. We'll be rolling out Mllo fully across all our calling surfaces and call types. We also intend to optimize it further to provide industry-leading call quality to our users for years to come. Thanks for listening to the talk. We hope you enjoyed it.
Wow, what a great talk. Thank you, Shriram, Hong, Jatin, and Vikash. I'd like to introduce our next talk, Improving International Calls, presented by Yi Zhang and Saish Girsapa, technical leaders for Meta's WhatsApp and remote presence orgs. Today, they will talk about the work to improve the reliability and quality of over 500 million daily international video and audio calls. E, with rich background in building RTC infrastructure for Meta's apps, and Saish, a veteran in networking and security who's been pivotal in scaling WhatsApp's call infrastructure. They are here to discuss Meta's investments in long-distance communication, ensuring every call is as clear and reliable as if it were local. Quick reminder that following this talk, we will have a live Q&A session moderated by Kostab, So don't forget to submit your questions on the at-scale conference websites, live stream chat. Now let's hear from E and Saish.
Hi, I'm Saish, and I build the infra that runs WhatsApp calls.
Hi, I'm Yi. I build the infra for Messenger and Instagram calls. We both specialize in building systems for real-time communication.
And we both work closely with each other to improve the call quality for all our users across the family of apps. And today, we're going to talk to you about improving international calls. I remember the first time I was on an international call. I was a young kid, probably around 6, crammed into a public phone booth with my whole family. We were calling relatives overseas. An LED display over the phone showed us in real time how much the call was costing us. It was ticking down precious minutes faster than I'd like. I don't remember the exact details of the conversation, but I clearly remember that the voices on the other end felt distant and muffled. And just a few minutes of the call cost us more than several ice cream cones. With the internet, international calling has come a long way. Calling apps like WhatsApp, Messenger, and Instagram enable us to call anyone, anywhere in the world for little to no cost. So much so that today, 1 in every 5 calls on our apps is an international call. That's about 500 million international calls a day, which is a staggering number. And while much of the focus over the years has been on driving down the cost of international calls, industry-wide progress on call quality has been lagging. Our analysis shows us that international calls are 20% more likely to be rated as bad by our users. So why is this? Not only are international calls more prone to quality issues, the technical challenges surrounding international calls are much more complex to solve. Let us see why some of these issues are so specific to international calls. Calls routed over the public internet have to deal with the limitations of the internet. Larger distances mean longer network paths and much more network hops. This leads to high latency and higher chances of packet loss and jitter. High latency manifests itself in the form of conversation lag. High packet loss can lead to video freezes and audio stalls. Other network issues like network congestion and jitter are also more likely to happen on international calls. Last year, we made significant investments in improving international calls at Meta, and this resulted in some impressive wins. During this talk, we will share with you how we were able to reduce network latency, improve bit rates, and reduce video freezes on international calls. For some country pairs, these improvements were in double-digit percentages. Before we get into the details of the new architecture, it will help to understand some of the basics of how calling works. Then we can go over the old architecture and see why it needed a redesign in the first place. E will help go over these topics first, and then I'll come back a little later to talk about the new architecture that now serves international calls. Over to you, Yi.
Thanks, Saish. Audio and video calls, like you may have guessed, are made up almost entirely of audio and video packets being exchanged between users in a call. Many devices connected to the internet are behind the network element, like a router or NAT. This can prevent them from establishing a direct connection with each other. Therefore, this makes it necessary to have a middleman or calling relay to help with this exchange of media packets. A calling relay sits in the middle and acts like a proxy between users and in a call. Each user in a call transmits media to relay, which in turn forwards it to all the peers. In an audio call, each user transmits just one media stream, but in a video call, each user transmits 2 streams, one for audio and one for video. Because the relay processes all the media packets, it is in a unique position to see all the packets. Then it can use this position to play a more active role to improve quality of the call. One of the advanced things that relay can do is to reduce packet loss. Let's take a look how it happens. Alice and Bob on a call with each other. Alice sends a packet, reach relay, but get dropped by the network on the way to Bob. This is called downstream packet loss, because this happened downstream of the relay. Bob was expecting a packet here, but doesn't see it, so he sends some feedback to Alice about this missing packet. This feedback is called a negative acknowledgement, or NAC. Normally, this NAC would travel back all the way to Alice, asking Alice to retransmit the packet. This is called retransmission from source, and it takes around 1 RTT, which is round trip time. However, a smart relay can help reduce this delay. It can cache packets that it sees. It can then intercept the next and respond to them by retransmitting the packet from the relay itself. This is called retransmission from the relay. Guess how much time does this save? It cuts the retransmission time in half, assuming the relay has equal distance to Alice and Bob. But what if the packet is lost on the first leg before even reaching to the relay? Again, the relay can be smart. It can detect a packet loss on behalf of Bob and send the leg back to Alice. Again, the retransmission time here will be cut by half, compared to if the relay had not been smart. There's a variety of the network conditions that relay can help. We already looked at how the relay can deal with downstream and upstream packet loss. Now let's take a look at a few other examples. The relay is also able to pace packets. If the downstream network is congested, they can help relieve some of the congestion there. If the downstream network shows a high packet loss, the relay can proactively duplicate the audio packets to reduce the chance of the audio stalls. We are still talking about all types of call here, but now let's take a look how the new challenges arise when we apply these same technologies to the new international calls. On international calls, the biggest difference is that Alice and Bob are far away from each other. Because of this distance, some of those congestion control techniques becomes a lot less effective. It takes much longer for the packet to be delivered over the longer distance. If the packet is lost, it is detected much later. Feedbacks like NAC takes much longer to reach the relay, and the retransmission, of course, takes longer to arrive. So reacting to network conditions like packet loss is much slower and less effective. And this is true for many other mechanisms on the relay, if we are talking about network congestion control and bandwidth estimation. Greater distance generally means more network hops. More hops leads to a higher chance of packet loss, network congestion, and jitters. So on international calls, we have more network issues, and reacting to them is much more difficult for the relay. So this is how it makes international calls so challenging. Now I will give it back to Saish to talk about how we redesign our architecture to address those challenges. Back to you, Saish.
Thanks, Yi. We spent a better part of last year building and rolling out a significant change to our routing architecture. And this was specifically for international calls. We call this cross-relay routing. With cross-relay routing, we make one important change. We add another relay to the mix. Instead of picking a relay that's halfway between the two users, we now pick two relays. Before we go into why two relays are better than one, it is important to understand how we pick these relays. Meta has hundreds of relays worldwide. In order to pick relays for calls, we maintain a large map of network latencies. This map contains the latency from every one of our relays to every network in the world. To pick two relays for an international call, we pick a relay that is closest to each user in terms of network latency. This style of picking relays has a rather surprising impact on call quality. Let us see why. Let's first start with an example of downstream packet loss. Every packet from Alice now traverses two relays to reach Bob. With this simple change of the additional relay, we have now increased the retransmission points from 2 to 3. We can retransmit packets from relay 2 or relay 1 or from the source. When the packet loss is on the last leg, then the relay closest to Bob retransmits the lost packet. This is significantly faster than before. In fact, because this is the relay that is closest to Bob, packet recovery times are now on par with local calls. What about upstream packet loss? That is, if the packet got lost on the way to relay 1. In this case, relay 1 generates a NAC, which results in a much quicker retransmission than before. This shrinks retransmission time to be on par with local calls again. This is great, isn't it? But you might still wonder, the packet could get dropped between relay 1 and 2. After all, that is the longest leg of the network path. So surely we'll run into the same issues as before if that happens. Now this is where it gets really interesting. Because these relays are part of Meta's infra, we have a lot more control over the network that connects them. And we have designed these networks to be of much higher quality. They are much more stable and high performing than the public internet. We call these network connections the Meta backbone. Meta has a global backbone network that spans pretty much the whole world and connects all of our relays worldwide. These links are dedicated for Meta use, and they were originally built to support our content delivery network. The backbone provides superior network characteristics like lower latency and lower packet loss. This makes it perfect for carrying real-time traffic. So in summary, by using a much higher quality network between relay 1 and relay 2, we can significantly reduce the chances of packet loss over the largest portion of the network path of the call. Relying on this existing network gives a big boost to international call quality. And this is great for international one-on-one calls. But group calls are another beast. I'll now hand it back to Yi to talk about how we can further enhance this architecture for group calls.
Thanks, Saish. Like Saish said, group calls add a bunch of new complexities. Many of those complexities are inherited from one-on-one calls, but get more complicated on group calls, especially on international ones. First, group calls has more users, which translate into more video and audio streams. More streams generally increase the chance of congestion. We need more advanced congestion control algorithms to react faster and address congestions more efficiently. Second, different users on different networks. This means there's a wide variety of network conditions. There's no single bit rate or algorithm that can be optimal for all the users. Our algorithm need to work with congestion control on a per user level rather than a per call level. Finally, in international group calls, user can be in 2, 3, or even more regions. This makes it a challenge to assign relays to a call. Assigning too few relays to a call would mean we don't benefit from the new architecture. But assigning too many relays to a call can increase the complexity a lot. In our previous group call architecture, we use a single relay server. All the users connect to the same relay, and the relay was responsible for transmitting media packets to all the users in the call in a selective forwarding way. In international group calls, users could be spread across multiple regions across the world, with a higher latency between them. We can sure apply the same cross-relay architecture to group calls as well. First, we assign multiple relays to a call that enable cross-relay routing. We assign one relay in each region of that user. We can call those relays local relays. They may not necessarily to be the relay closest to the user like them in one-on-one international calls. Assigning too many relays to a call can make the system and algorithm very complicated. Second, we assign a central relay to the call. All the local relays forward the packet to a central relay. The central relay has a view of an entire call and can make centralized decisions. In terms of the algorithms, moving congestion control algorithm to the local relays is most effective. They detect and react to network conditions much faster. On the other end, selective forwarding algorithms can only function in a centralized way because they need a full view of the entire call, so they can only run in a central relay. Now, let's take a look at the congestion control algorithms. The local relay is mainly responsible for downstream and upstream congestion control. It deals with one or more users in the call, but not the whole call. It detects and reacts individual network conditions for each user. Let's take a look at a few examples. The pacer is responsible for managing the spacing between packets. This helps reduce jitter and packet loss on the downstream. Another example is the retransmitter, which also works on the downstream side. This is responsible for caching packets and retransmitting them in case of packet loss. On the upstream, the retransmitter requester It monitors the sequence numbers of received packets and spots missing packets, then generates a NAC for the missing packet and sends it upstream. The central relay is responsible for select forward. Select forwarding is the process of deciding where to send the packet and whether to send the packet. The central relay uses a variety of the inputs to make select forwarding decisions. Many of the inputs are feedbacks received from no-code relays. Let's take a look. Bandwidth allocator relies on the bandwidth estimates for individual users. These estimates are calculated on the no-code relays in a central relay. Then allocator uses those estimates to compute the optimal bandwidth allocation for each user. It can help adjust the bitrate of the call based on available bandwidth for entire session. The simulcast module deals with the inconsistent network conditions between users in a call. Only some users in call may have more congested networks. Local relays mirror this and send this information to central relay. The simulcast module then sends a low bitrate streams to the congested users and high bitrate to the users on the better networks. This optimizes the call quality for each user based on their own network conditions. Now, I will let Saish go over the current state of the architecture and some of the results we have observed.
Thanks, Yi. WhatsApp, Instagram, and Messenger have all benefited immensely from this new architecture. WhatsApp is rolling out this new architecture specifically for one-on-one calls, while Messenger and Instagram have fully rolled out this architecture for all group calls worldwide. We ran experiments to verify the results as we rolled out these architectural changes. We observed statistically significant improvements in many call quality metrics. The results did vary across products and across country pairs. Here is a glimpse into the kind of results that we saw. We were able to reduce feedback latency by over 40%. This made congestion control algorithms way more effective, which in turn improved call quality. Bandwidth estimation improved so much that video calls were able to use much higher bit rates, as much as 5% higher. Video freezes reduced significantly by up to 15% on certain products. If you could walk away with just one takeaway from this talk, it should be that congestion control mechanisms are far more effective when running closer to the user. And the effectiveness of these congestion control mechanisms can play an outsized role in call quality. To improve call quality for international calls, we can use architectures like cross relays to move these mechanisms much closer to the end user. For Meta specifically, having more control over large parts of the network path further helps improve call quality. And there are security benefits to routing calls over a dedicated network. But there are downsides too. Adding more active hops results in increased resource utilization. This may not seem like much, but at Meta's scale of billions of calls a day, these cost increases can be pretty significant. Some routes benefit a lot more than others from cross-relay routing. In fact, some route might even see regressions from this architecture. This is because of oddities in the network path that packets take over long distances. We did find a few surprises like this during rollout, and that caused us to take a step back and then make our solutions much more adaptive than before. And finally, we have many more improvements in store in the years ahead, which will help us build on the work that we have done so far. We are working on adding new forms of congestion control, as well as refining and optimizing the algorithms that we already have. We are also working on ways to improve the security of cross-relay traffic using protocols like QUIC. We will continue to work on improving the quality of international calls in our mission to help connect the world a little better.
Good morning, everyone, from Seattle here. My name is Kaustubh. I'm a research scientist in the audio team here in Seattle. I will be the moderator for the talk today, and I want to start by thanking all the wonderful speakers, and I want to thank all the audience for getting up early in the morning, if you are in US, or late at night if you're somewhere else. I want to thank the speakers, and I want to get straight to the questions. If you have not already asked a question and you want to ask a question, there are many channels through which you can go. and I will try to get as many of these answered as possible. So let me start with, there are some questions on the line. Let me start with the first one. This question is for you, Sriram. And the question is, it will be interesting to know if this is Barrel and Mllo is already introduced in production. How was it introduced? And the complexity of rollout across many devices, limited pilots for forgiving customers, and willingness to provide feedback, and then the introduction of new versions based on the feedback. Long question, but stage is yours, Sriram.
No, that's a great question. Thanks for asking that. For us, not disrupting the user experience, that's P0. Barrel and Mllo are actually both rolled out to our users, to a large majority of our users across Messenger, Instagram, WhatsApp. There's some pockets that we're still rolling out to, but vast majority of our users are getting Mllo already, especially on Android. The similar story with Barrel echo cancellation. So having answered that out of the way, the second part was how did we stage the rollout, right, without disrupting the user experience. So let me answer this in two ways. We actually took a two-step approach for this. First, we built a very rigorous offline test framework to make sure that we were fully prepared before going live. So this meant building a very representative data set that's close to what a users experience. We never collect audio data from our user calls. They're all end-to-end encrypted, and we just don't collect data from our user calls. So that means we leveraged open source collections of voice data, different noise conditions, multiple languages, built up a very thorough data set that we had confidence in. Then we would test our algorithms on this, and to evaluate them, in addition to any objective metrics that we're used to, we regularly performed crowdsourced subjective evaluations throughout the development process, because this is telling us how the users actually perceive the quality, either for the codec or for the echo canceller, when they're listening to it on their own devices, in their own acoustic conditions. So this gave us a lot of confidence before getting into public testing, right? So you don't want to have too many iterations in public testing because you can't collect audio data. You work off some technical metrics, but high confidence going into the test, main reason also being not disrupting the user experience. Now that we completed all the offline tests to our satisfaction, then we started rolling out Barrel and Mllo to a very small slice of our users, perform very careful A/B testing, make sure your CPU, memory, crash, all of that is under control, and then look at key engagement metrics. Once they are good, then we slowly ramp up until we roll out to the full population. So this is kind of how we staged it, building confidence offline, testing in production, and then gradually, incrementally ramping up to not disrupt user experience. And we were really, really happy to see positive engagement metric wins as we started these rollouts.
Thank you, Sriram. The next question is for you, Hong. Is it possible to dynamically switch between two modes of Barrel on the fly? Example, detecting overload on the system. Could you switch to the light mode to save CPU?
Yeah. Thanks for tuning in, and that's a great question. The short answer is no, as currently the two modes that we have come with its own filter design and configuration, and we need to initialize those when the call starts. But definitely that is something that we will be looking into, as complexity does vary dynamically depending on are the apps running at the same time or the battery health of the device. So definitely that is something we will be looking into.
Thanks, Hong. Jatin, the next question is for you. It's a difficult one, as this person says. You end up with RTP header, etc., taking more data than the audio itself. Is this where moving away from RTP will help the media over quick, etc.? It's a huge, interesting space.
Yeah, thanks for asking. That's a great question indeed. So you are right, at the lowest bit rates, we do care about the RTP header overhead itself, and it can easily add up to 5 to 10 kilobits per second, depending on the packet sizes you are using. But within Meta, we are able to use some novel techniques to reduce that header overhead, even while sticking with the RTP protocol, because that has been proven to work well. But at the same time, there is, as you said, there is huge interest in the community, and within Meta, we have a dedicated effort to experiment with Quick and evaluate how we can get more out of Quick in all of the Meta products. Yeah, hopefully you will get to hear more about that soon, like we launching Quick to some of the apps.
Thanks, Jatin. And there is a follow-up to that. The speaker says, I can't help but wonder how much more redundancy encoding this new audio encoder requires to ensure error concealment as effective as Opus.
Yeah, another great question. So interestingly, Mllo also has most of the salient features which Opus has, like in-band FEC is one of the very standard ones. So we added that for Mllo from the very beginning. The best part is, since Mllo is able to encode very high quality at the very low bit rates, we are in fact able to start encoding redundant audio at lower total target bit rates than even Opus. As a result, we see that we are able to recover more lossy audio in production with Mllo as compared to Opus. And the production results from our experiments kind of do share the same story. So it is possible, and on the FEC part as well, it's superior than Opus.
Thanks, Jatin. Because the next question is up for you. I'm rephrasing it a little bit. Is it worth, the reader asks, is it worth to NAC audio packets? For videos, I see a reason, but for audio, it would be good to have some more comparisons.
That's a great question. Thank you. Thanks for asking. So Jatin talked a little bit about the FEC part. We have seen that if the network is lossy, but we have much shorter round trip time, then NACs can be really effective. Also, something to note is that NACs are always higher quality than in-band FEC. So if you can use it effectively, it can provide better quality. So therefore, like we use a combination of techniques. As you can imagine, our user base is in very diverse on different network conditions, different devices. So we use combination of these different technologies, NACs, FECs, to optimize the call quality. Thank you.
Saish, the next question is for you. Why is the central relay taking all these bandwidth estimations, temporal and simulcast decisions? Why not add these capabilities to all the relays?
That's a very interesting question. Yeah, we do bandwidth estimation at the local relays, but I think what you're talking about is bandwidth allocation, which is done only at the central relay. This is because bandwidth allocation has to take into account bandwidth estimates from all users, and it has to decide what is optimal for the entire call. Bandwidth allocation is a process by which we decide how much bit rates the user should be sending, not just how much they should be receiving. And so this has to be decided at the central relay. It is the same with temporal and simulcast decisions. Deciding whether to use simulcast and how much bitrate for those streams has to be decided centrally, because it again requires understanding of the network conditions of every user in the call. It's not that these decisions cannot be made locally. It's just that to make the decision locally, there's a lot more information that needs to pass between all the local relays, which would result in much higher chattiness of the protocol and also much higher latency.
Thanks, Saish. The next question for Yi. Is there an international group call with 10 or 15 participants? How many relays would you assign to such a call? How do you decide which relays you want to assign?
Thanks for the question. So this is a great question. As for international group calls, no matter how many participants in a call, we actually assign the user to the closest relay. So we divide the relays clusters into multiple different regions. So that if the user geographically within the same region, so they will be assigned to the relay cluster, same relay cluster. Yeah, I think that's the answer.
Thanks. Because next question about Mllo for you. Are Mllo and Barrel rolled out to desktop browser clients yet?
Thanks for the question. As Sriram mentioned earlier, we follow a gradual rollout process to ensure that we are delivering these new innovations with a very high quality bar. Therefore, we started the rollout on mobile platform because that's where a majority of our user base is. We will look into the other platforms in the future. Thank you.
Shriram, next question is for you. How does Mllo audio codec extend to immersive or spatial audio encoding experiences?
That's a good question. As we heard in Nitin's keynote, spatial immersive and metaverse scenarios are key to our mission. That said, the innovation in Mllo that we targeted was for the low bitrate segments, which is where across our family of apps for calling, we felt the strongest need was to deliver high quality audio to all our users across all geos, including the lowest bandwidth tiers. And the strongest need there to innovate and provide greater quality was in the low bitrate segments, mainly targeting speech. And doing all of this without increasing compute, like we saw in Jatin and Bikash's talk. Other than that, I will say though that Mllo supports stereo, it supports multi-channel encode decode, all in a manner comparable to Opus.
Thanks, Shriram. Saish, the next question's for you. The person asks, in a multi-party call, how do you decide the central relay's geographical location? Can the central relay be eliminated eventually?
That's a great question. And that is something that we've thought about a lot. So the first part of the question is, how do we decide the location of the central relay? Now, this is a fairly complex way of determining where the central relay's location should be. This is because once a call starts, and it's very hard to relocate the central relay as the group call changes. So we have to assign the central relay fairly early into the call. And this means we have to make certain predictive decisions. We try and place a central relay closer to a hub, which is better connected network-wise. And then we cannot change it as the group call changes because it can be disruptive to the call. In terms of eliminating the central relay, we are trying to see if some of our algorithms can be made more distributed, but so far it's a fairly complex challenge. So we are for now focused on keeping it more central, but we are looking into certain algorithms. For example, audio capping is something that can be made more distributed. Hope that helps.
Give me a minute. I'm just going through the list of questions that are being added quick. Here is one for Hong. Any gotchas you would like to share when implementing Barrel AEC in real time?
Yeah, so threading issue is one of the gotchas that really stood out for us when we implement Barrel in production. It's very hard to debug threading issues. And basically what we encounter was some audio artifacts and pop and clicks. And it was due to some shared memory buffer used in our FFT routine that got accessed concurrently between both the capture and render threads. And it took us a long time to figure out, and we needed to do some audio dumping at different stages of the algorithm to really narrow down the issue. So please pay attention to threading issue.
Awesome. Following up with Jatin, what do you think is the most challenging task during Mllo quality evaluation?
Yeah, thanks for asking. That's a good one. So inherently, evaluating audio quality is pretty tough. Since it's all about how the humans are perceiving it, it's really a subjective thing. Yeah. There are existing tools out there Whisker and Polka, which help you evaluate the quality in an objective manner, where you provide a reference signal and a test signal, and it can tell you a Mohs score in the range of 1 to 5. But end of the day, these tools are objective. They are trained on certain data sets, so they are not able to capture subtle differences between the audio signals. One of the main challenges we ran into was being able to reliably tell that, hey, we are able to improve the audio quality, as we are in the development process. So it would often require you to listen to some of those samples manually to make sure those are actually sounding better with the improvements you are just adding as compared to before. This also makes you ear deaf to repeat listening to the same signal again and again. which makes it also harder. So that's for the development part. For the evaluation, similarly, as a very standard process in the codec development, we didn't rely on using the objective tools as the only measure. We went ahead and did the crowdsource-based subjective listening test. Those were very large-scale listening tests where we evaluated literally hundreds of thousands of audio files across many different listeners of different EGs and all. So the crowdsource listening tests, they are very time consuming, they are very expensive. So you can only do those so often. So you need to strike a good balance of how you're able to get most out of those while still being able to evaluate the quality fairly.
Thanks, Jatin. Next question for you, Sriram. How do you see ML algorithms for meta apps? The methods you spoke of today were mostly DSP based.
Yeah, it's an interesting question. I think I touched upon it a little bit in the talk. We at Meta obviously believe a lot in the promise of ML, and we've been leveraging that already, also for our audio algorithms. And we're taking a very judicious aspect to it, right? So ML is a very, very powerful tool, and we use it where it actually leverages, where it brings user benefits. And our main goal is to see how can we benefit the user. If we benefit a large proportion of our user base using DSP, we'll do that. If we can do that using ML, we'll also do that. So one way to look at it is on capable devices, we are already leveraging ML-based echo cancellation, for instance. The interesting thing, though, is at our scale, low-end devices are a huge proportion. So what may be a corner case is still millions of users for us, right? And from some of our experiments, even within DSP algorithms, if you are increasing complexity by, say, 10, 15, 20%, you start to see that getting reflected in engagement metrics. So we've got to be really, really judicious. So our approach is have a really good baseline solution that gives you very good quality, regardless of whatever device or network you are in, right? So even if you're on a low-end ARM v7 devices, you'd be surprised that we still have a lot of our users on those devices. We give really good quality. But at the same time, if you're on one of the high-end devices or you're on a desktop, these days high-end mobile phones are often even more powerful than some desktops, then we also want to make use of that CPU, and there we are leveraging ML solutions. Meta is a leader in the ML space, and we have very good audio algorithms, including echo, noise suppression, etc., running using machine learned models.
Thank you very much, Sriram. Yi, the next question's up for you. In group international calls, could the network between the relays actually cause more delay and worse quality if the network itself isn't powerful enough?
Yeah, thank you for the question. I think this is very interesting. So first of all, our between the relays and the central relays, we are running inside of the FB, the Meta's backbone network. So by design, we believe in general, it has more bandwidth and less packet loss compared to the public internet. The second is that we are also working on improving the Meta backbone, such as we are currently having a hop-by-hop NAC buffers between the relay and the central relays. So any packet loss, we can recover from the central relays. And also we're working on adding a quick transport between the relay and the central relay. We're hoping using the quick internal congestion control mechanism can help, will make the backbone more reliable.
Thanks. Sesh, the next question is for you. If the central relay is not close enough to a participant, does that mean all these decisions like bandwidth estimation, congestion detection are also delayed?
That's a very good question. So I just want to remind you that we do in fact do bandwidth estimation and congestion control on the local relays, not at the central relay. And these decisions need to be much more real time to prevent deterioration in call quality that are coming from variable network conditions. The decisions that we do make at the central relay there's no need for them to be as real time. They need to be quick still. An example of this is like deciding if simulcast needs to be used for the call. And delaying these decisions a little bit does not have as big an impact on the call as, say, congestion control. at least in our experience. And especially we can reduce the impact of that by being conservative with these decisions, like sending lower bitrate than what is required. The main reason we keep them on the center relay is because these need information from the entire call, not just from a single user. And so right now we haven't figured out a way to make them distributed enough to move them to local relays.
Thanks. Jatin, the next question is up for you. While I understood that Barrel is fully implemented in software and does not leverage hardware, the person asked, correct me if I'm wrong. What is the case with Mllo? There is a lot of devices with very good DSP and hardware acceleration for codecs.
Yeah, that's an excellent question. So yeah, as you rightly guessed, Barrel and Mllo, they are not done in hardware. Given the time span we are operating, like, everything getting out of the door in a matter of, a couple of quarters, it's pretty much out of scope to, consider doing hardware implementations and, and then the users' latest handsets need to support those hardware implementations to be able to, fully use it. So Barrel is no doubt is fully software. Similarly, Mllo. But we are able to use the neon optimizations, SIMD optimizations to squeeze out maximum out of the available CPU architectures at hand. As an example, there are also not many hardware implementations available out there for the audio codecs. EVS, which has been out there for a long time, and that is the only one which has a hardware implementation we are aware of. Opus, even it is the global standard, it still does not have a hardware implementation available out there. So you can think that it is not super common for audio codecs to have hardware implementation. Yeah.
Yeah, just to add on to it, Kostub, Jatin, you touched on all the important things. I think one of the things to also keep in mind here is for VoIP, it can make sense if you have the entire processing happening in hardware. You don't want to have back and forths between hardware and software, then you're kind of losing the main benefits. So if you're able to get the entire encoded bit stream from hardware, that makes sense. But we have a bunch of software processing happening anyway. And so a better way is to make use of all the SIMD optimizations that Jatin alluded to. This is where you see in the PSTN or the cellular case, codecs like AMR or EVS, they are all happening in the baseband chip because everything is happening in hardware there. If we have to also go back and forth between software, like is the case in VoIP, we prefer to do this in software with hardware acceleration, like Jatin pointed to. Echo traditionally has been a different case because, you have the audio capture happening on the chip, echo noise happening in hardware, and then you get the PCM. No more going back to hardware, but for codec, it's a slightly different use case.
Thanks, Sriram and Jatin, for that response. We'll do 2 rapid fire questions before we run out of time. For Saish, do the relays transcode the stream before relaying it or pass it through?
Good question. So we don't do any kind of transcoding on the relay. In fact, on WhatsApp, all calls are end-to-end encrypted, which means we have no access to the contents of the packet to like decode or re-encode them. So there's no transcoding at all on the relay. Even when it's possible, we like to keep our infrastructure uniform so that they have the same capabilities. So we don't plan to do any transcoding on the relay.
And the last question, this is for Yi. What's the main benefit to run mix of send, receive BWE on the relay compared to just using TWCC on send side?
This is a good question. I think for the send side, we know the benefits. It can help the client to understand their uplink, and for the relay to understand the downlink. The receive side is more on the relay side to determine what's the received bitrate. So we're using a remote bitrate estimator to estimate the bitrate for the uplink, which is from the client to the relay. Then we can using this information to fit into our bandwidth allocator in the central relay. Then we're using those information to help make the better decisions on the central relay for the bandwidth allocation, such as simulcast, sample layer, all based on those bandwidth allocation results.
Thank you very much. And I would like to thank all our speakers, Sriram, Huang, Jatin, Bikash, Yi, Saish, not only for your wonderful talks, but taking the time to answer these questions. Thank you very much to all the audiences, and hope you have a wonderful RTC at Scale 2024.
What an incredible Q&A session. A big thank you to everyone for your insightful questions. We'll now take a quick break. See you back shortly. Welcome back. We're excited to dive into our second session block, focusing on next-gen RTC video. Our next presentation will be led by Shyam Sadawani. Shyam will talk about Meta's approach to ensure high-definition experiences on advanced networks and also for calls in poor network conditions. Shyam has a rich background that spans over 25 years in video compression technologies, including leading roles at Microsoft and contributions to MPEG encoders and stream analyzers. I'm also lucky to partner with him for the last 7 years on real-time communication products for Meta. Over to you, Shyam.
Hi, I'm Shyam Sadwani, a software engineer in remote presence in Meta team. I use video calling apps like billions of users to connect to my family and friend. The audio and video quality are super important for these scenarios. Often I wondered why the quality is not as great as, let's say, Netflix streaming. I use the same network, same devices, I get very good quality during the streaming, but when I make the real-time communication call, almost feels like it could be better. Luckily, I get to work on these apps on daily basis. And we explored a lot what are the challenges. And in this presentation, I'll be sharing what we learned, how we are mitigating those, and what we did for some of them. So before we jump onto that, let's look at the brief history of how things progressed in last decade. So if we look at some of the scenarios, for example, DVDs launched in 97, they added 1080p Blu-ray and then 4K in 2016. And YouTube, which is a streaming service, the first major streaming service, started in 2005, but they have been able to add 4K in 2010. So some of these services, they have seen accelerated growth. Now, if we look at the devices and network improved, but for real-time communication, the quality is still lagging behind. Often, one of the questions we get is, I have 1 gigabit network. I can stream 4K videos. But when I make a real-time call, the quality is blocky or it's not as great. The video is not smooth. So let's look at some of the obvious ones. Now, real-time communication calls, a lot of them are running on mobile devices and they are running on a battery. And a lot has to be done for these apps. They have to capture video, encode video, encrypt, send it over the network. At the same time, they are also receiving, decrypting, decoding, and rendering them in real time, both audio and videos. Also, there are other services running like the network bandwidth estimation. And all of this has to be accomplished in slow latency, ideally below 300 milliseconds, for a great calling experience. To do all of that on a battery and low resource usage is challenging. Also, these apps and these scenarios, they lack the luxury of server processing or any offline processing. So we drill down into some of the non-obvious ones in the rest of these presentations. Now, one thing we learned was the problems and the solutions are very different when you look at two ends of the spectrum, the low-end networks and the high-end network. In this presentation, we'll be covering both of them. Let's start with the low-end network first. So there is no universal definition for low-end and high-end, and it depends from scenarios and users and the applications. What we define low-end for this presentation is the users who have below 300 kbps bandwidth. The users between 300 and 800 is like mid-end, and above 800 is high-end or HD capable networks. Now, a lot of time people get surprises that video calls are using 50 kbps or even 25 kbps these days in these network conditions. Note, this is the share that video encoders get of the overall network pipe, which gets shared between audio codecs, the signaling overhead, retransmissions, RTP overhead, duplications, and FEC. Now, the big assumption here is the bandwidth estimation, which estimates the network pipe, is working correctly. It's a complex topic on its own, which is outside the scope of this presentation. So next, we looked at what options we have for these low-end networks. Now, the biggest one which stands out is to use an efficient codec like AV1. We also looked at some of the other smaller ones like video enhancements. For example, the video scalers which come with WebRTC, they provide a reasonable quality, but they don't provide the best quality. So we improved the scalers. We also worked on the region of interest encoding. So in this one, you identify the region, which in RTC case happens to be the talking head, and we spend more bits on those. So with these ones, we saw incremental quality improvements. We are also looking at some of the advanced processing, like the frame rate interpolation and super resolution. These provide significant quality, but they take a lot of resources. So what we found was the codecs is one area where we need to invest in. Let's quickly look at brief history of the video codecs. H.264 has been one of the most popular and supported codec in last decade, but it's still 20-year-old codec. Last year, Nicholas from our team, they gave a talk, and he said our plans to deploy AV1. Since then, we have been able to deploy AV1 on mobile devices, but it was not easy. We hit a lot of challenges and we had to mitigate a lot of issues. But let me first explain why we chose and how we chose AV1 as the next codec. So one of the things which surprises a lot of people is when we go and tell them that we are still using software encoders and decoders. Now, what are the reasons? If you look, H.264 and even H.265 is available in most mobile devices, and it's supported in hardware which can do very low battery usage and can do 4K 60 FPS real-time encode and provide very high quality. But when we compare these codecs to do a real-time communication scenario, for example, 7 FPS or 180p and 200 kbps encoding, we found that the quality of the encoder is not as good as a software encoders. And the main reason is the prioritization. Most IHVs and hardware manufacturers are not even aware of the network conditions in which RTC calls operate even today. I'm sure things will improve, but till then we have to rely on the software codec. Hence we chose AV1, given the licensing cost, given that it has tools for RTC scenarios, and overall quality versus performance trade-offs. Let's first look at the quality aspect of AV1. So here is a subjective quality evaluation where we are comparing AV1 at 25 kbps and 264 side by side. As you can see, AV1 is providing much better quality, less blocky, and you can see background and face very clearly. This is very important for RTC scenarios. Some of these may not be obvious in the presentation, so I have all the links in my blog. Please refer to them offline so that you can check the quality side by side. In addition to subjective, we also did the systemic quality comparison. Now the standard method is rate distortion graphs. So in this one, the horizontal axis is the video bitrate and the vertical axis is the PSNR. What we found was when we compared AV1 to 264, AV1 outperformed 264 at pretty much all the presets. Roughly it provided 2 dB quality improvement, or if we keep the quality same, we can reduce the bitrate by 30%. For screen sharing, we saw even more improvements, which is not surprising as AV1 has screen sharing specific tools. So now we were convinced that AV1 is better codec and probably the right choice for RTC. We needed to run public test. Before we could start public test, we hit an issue, which was the binary size increase. AV1 adds 600 kilobyte to our binary. This is a significant increase as it impacts the download and install experience for people, especially on the low-end devices and networks. We analyzed the binary and we found some low-hanging fruits like the quantization tables, which were contributing about 10% of the overall AV1 codec binary. We have fixed these issues and are also working with Google to improve this on the future codecs. The other issue we were anticipating was the battery regressions. Based on our lab test, we saw around 4% battery regressions with AV1. These are very serious. A lot of RTC calls, they end because people run out of battery or people hang up once they see low battery notification like you get typically when the battery is below 20%. So in order to mitigate this, we tackled the problem several ways. First was device filtering. We filtered out the devices with low-end battery or low-end CPUs. We did codec optimization to improve the CPU performance. And the last one was we use WebRTC and SDP for the codec negotiation. So we negotiate multiple codecs like AV1 and 264 upfront, and then we are able to switch the codec on the fly based on the CPU and battery levels of the devices. This even allows asymmetric codec, where one side could be sending AV1 and another side could be sending 264 based on the battery levels of devices. We hit some out-of-memory crashes because of increase in memory usage. For this, we filtered out the devices with low-end memory, but this is an area for improvement which we are also working on for optimizing the memory usage. So the next challenge we faced was how do we confirm that people or our users are actually getting high quality? For that, we needed a real-time metric that we can implement and measure the quality. We have been using composite metric, which combines things like encoding bitrate, frame rate, quantization parameters, and generates the video quality score. But this cannot be used since the quantization parameter is not comparable between AV1 and 264. PSNR is industry standard metric, but it requires the reference videos and does not work for RTC. There are non-reference based metrics which we are exploring, but they are resource intensive and are not available yet. So we had to rely on some new metrics. We came up with a scheme for this and we have been able to use PSNR for real-time communication. Now how we did this was, we came up with a framework where we generate the rate distortion from the encoders caused by the compression, and we generated similar distortion caused by the scalars. These are the two main components which introduce the distortion in the sending error encoding pipeline. We have been able to combine these two together to generate the final PSNR value. We verified in the lab test that the PSNR is very accurate and close enough to the real PSNR as if we had the references available. We will be sharing our findings and learnings in academic publications. But with this low complexity PSNR metric, we have been able to confirm 2 dB quality improvement when we moved from H264 to AV1. With all these mitigations, we have been able to deploy AV1 on iOS and Android devices. We have not completely replaced 264 and are working on improving the coverage, which I'll be covering later. Next, we looked at how we can improve things for the high-end network. So far, we have been talking about people with low-end networks like 3G, but a lot of people have very good networks like 5G and 100 Mbps. Just to recall, what we mean by high-end are the networks where bandwidth is above 800 kbps. Modern devices, they are able to capture 48 megapixels. And the expectations for people are to be able to get HD quality videos similar to Netflix, YouTube, or Reels. We ran some local tests. We want to provide the local camera record-like quality in RTC scenarios. What we found was a bitrate of around 3.5 megabits, 30 FPS video, and around 720p provides the quality at par with the local camera recordings. Now, 60 FPS provides much better quality than 30. The video looks smooth, but there are challenges, which I'll be covering later. 1080p looks better, especially on the devices which have bigger displays. But what we found was majority of the devices, people don't see any difference between 1080 and 720. Now, a lot of people wonder, why is it not a simple configuration change or the camera settings change to change the encoding bit rates and to change the capture resolutions? It's not very simple, especially if you run a public test at scale with millions of devices and you collect a lot of metrics. So in the first iteration, when we ran these tests, we saw a huge regressions in talk time. We saw regression in network metrics like the packet drop rate, call drop rates, and we saw increase in robotic audio or 1-star ratings, people survey results. We drilled down into the reasons and mitigations. I'll be sharing some of those. So for example, one thing we learned was oscillations are really bad. By oscillations, I mean the oscillations in video quality. So these happen when users see high quality video for some time and then really low quality video. These are worse than providing a stable low quality video for majority of the users. Now to fix this, we had to modify our bandwidth estimation algorithms to build heuristics and to modify the algorithms to be able to avoid these oscillations. Other thing we learned was, as you can see in this network pipe, the higher the network bandwidth you use, you are exposing your both network adaptation and bandwidth estimation algorithms to a bigger problem space. If you use very low bandwidth, you are not going to hit any congestion. If you use higher bandwidth, you will hit more and more of these congestions and your algorithm will be tested more and more. So for example, one thing we had to implement was ISP network throttling detection, which is not caught by the standard delay-based estimation which ships with WebRTC. Now bandwidth estimation is an area where all of these apps, they try to distinguish and they have their custom implementation for the devices and network. Other thing we learned was the audio quality matters a lot more than the video, and especially at 2.5 megabits or higher, we can afford to have 2x or 3x audio duplication on FEC to avoid any regressions in the audio quality. We found that on cellular network, we hit more of these congestions and audio regressions. So we disabled high quality modes on cellular connection. We relied on machine learning based device targeting and HD targeting, where we look at the previous call histories and are able to build heuristic whether to enable or not high quality mode at the beginning of the call. Next, we ran further iterations with these mitigations. Now we have a lot of metrics when we run these public tests. For example, we collect performance metrics like the CPU, battery, network metrics like RTT, packet loss, and for the quality, things like video freeze, robotic audio, and video quality scores. One thing we found was regressions in battery, and they came from the camera capture FPS. Most of these regressions were not caused by increase in bitrate or increase in resolution, but from the camera capture frame rates. This is the reason we were not able to ship 60 frame FPS. Instead, we rely on 30 FPS or even go down to 24 FPS, depending on the battery conditions. To mitigate some of them, we built an infrastructure where we detect things like the device model, battery level, whether devices are on cellular or on Wi-Fi, and we aggregate this information, and we also do real-time monitoring as some of these things can change during the call, and based on that we are able to switch between a high quality mode and the power saving mode, whether either side is on a cellular, Wi-Fi, or these capabilities. Other thing we found was some of the devices are not able to keep up with the high memory requirements for these high quality modes, so we filtered out the devices with the low end memories. So with all of these mitigations and improvements, we were able to launch high quality HD calling experience on iOS. We are not completely done. We think there is a huge scope for improvement. Now to sum up and to recap quickly. So for the low end network, we saw good benefits of using AV1 codec. There is a good industry momentum where iPhone 15 Pro is supporting hardware decode, Pixel 8 is supporting both encoders and decoders. We plan to leverage them. There is opportunity to use machine learning and AI to do things like video processing, video enhancement on the receiver side. Super resolution is one of them. Frame rate interpolation is another. Meta has really cool demos for the codec avatar. So these are where you build a model for human and you transmit that model once, and then during the call we are transmitting audio and we are transmitting just the video vectors instead of the full traditional encoded images, and these provide very low bandwidth video calling experiences. I have some links in my blog for some of these demos for the codec avatar. Please look at those. Now for the high-end networks, what we learned was, in order to leverage the increased network and device capabilities, you have to do a lot of work. It's not as easy as just changing the setting and change the setting of network bandwidth or the camera capture frame rate. The main thing is the bandwidth estimation has to keep evolving with the improvements in the network. For this, we are leveraging machine learning based algorithms to improve our network bandwidth estimation. For the codecs, for HD and high resolution, we have to leverage hardware codecs, as the software codecs cannot be used for these more complex and advanced codecs. So we still need to use software codecs as a fallback when we hit the reliability and stability issues in the hardware, and we will keep on maintaining both of them. Most modern devices, they are adding functionality and features in the camera and video processing to distinguish and provide competitive advantage. We keep on using those, and these are one of the keys to leverage the hardware to provide better experience for the end users. So products and the infrastructure will try to make the best decision when it comes to the quality versus data versus performance trade-offs. But at the end, users need to have the final control via some settings or the UI control. Now, one thing we find is there is a huge opportunity to improve real-time communication scenario, and that lies in a good collaboration with the hardware manufacturers. The settings or the network conditions in which these calls operate today are new or unknown to the hardware manufacturers. We feel like working closely with the hardware manufacturers, if we can improve the quality for hardware encoders to work really well in these low-end networks, and especially for the newer codecs which are upcoming like AV1 and AV2, this will open up really great RTC calling experience for billions of people who are moving away from PSTN calling to the video calling. That concludes my presentation. Thank you.
Thank you, Shyam. Up next, I'm thrilled to welcome Thomas Davis to talk about AV1 and the challenges for delivering a next-generation codec for RTC. This talk will explore the unique challenges of developing and deploying the AV1 codec within real-time communication applications. Thomas has more than 20 years of experience in video coding for a variety of applications, including leading AV1's deployment at Cisco WebEx. Anyone interested in future of video encoding will find his insights very valuable. Please join me in welcoming Thomas.
Hi there, I'm Thomas Davis, and I'm here to talk to you about AV1 at the coalface, so developing a practical RTC solution using AV1. I started working on AV1 by developing the standard, and since then I've been eating my own dog food and developing production encoders for AV1. Now, when I started on video coding, RTC meant video calling, conferencing, that kind of thing. But since then, the scope of RTC has increased to include things like gaming, sharing, and live streaming. So it's become increasingly challenging to develop an AV1 encoder for that range of applications. So my agenda today will explore some of the issues that come up in that development. So first of all, I'm going to talk about what's involved in rolling out a new codec and what requirements does that impose on an encoding solution. Then I'll talk about some of the key challenges in meeting those requirements, especially with an advanced codec like AV1. I'll talk about where we've got to with Aurora 1 RTC, and then I'll have some comments about what the future looks like, especially with ML tools and ML enhancement and ML encoding. And then I'll leave you with some takeaways. So for a codec rollout, you need to answer 3 basic questions: what, why, and how. Now, what means characterizing your application from the perspective of a video encoder. So that means what bit rates and resolutions are you supporting? What is your performance envelope, particularly in software? That means how much CPU you can use on each kind of device that you want to support. It also means what content type you're targeting, whether that's standard conferencing or live streaming or screen content, and what latencies you need to support. So that might be standard 0 latency, or you might be able to have slightly higher latencies, maybe a quarter of a second or so, for some streaming applications. Then you need to ask yourself why, of course. What is broken? What do you want to fix? What do you want to improve? So that might be you need to provide better quality for screen content, or it could be that you maybe have some mobile clients in your application who are experiencing a high degree of loss, or in some circumstances can't get video at all because over UDP transports they're losing too many frames because of variable bit rates. And being able to lower the bit rates that you're using a lot may improve that resilience considerably. So if you have this rationale for what you want to do, then you can plan how you're going to do it. So that means thinking about where in that bitrate resolution ladder your new solution is going to fit in. So typically a new codec like AV1 will give you bigger gains at lower bit rates and at higher resolutions. So you need to find a sweet spot, but you may also need to have adequate performance across a whole range of bitrate and resolutions. And the more flexible your solution is, the more performant it is across that range, the easier that is. The other thing is, what CPU envelope can you actually support? Can you afford to spend a little bit more on your new codec, or are you fully constrained by what you currently have? And those things might tell you whether or not you have a dynamic deployment model where you are changing your codec on the fly, or whether it's more static and you're moving the whole system onto the new codec. With that model in mind, that helps focus us on some of the challenges that we faced in developing Aurora 1 and that anyone will face in developing an RTC encoding solution. I want to pick out 3 today. That is around performance, around rate control, and about some of the adaptive behaviors that AV1 supports. So what do I mean by performance? When people talk about video encoders, they often mean something like you can get X% bitrate saving over such and such an encoder, 50% or 20% or whatever. But in practice, especially when you're talking about RTC, there's what I would call a waterfall curve, where you have a relationship between the quality that you can achieve and the complexity required to achieve it, as measured here by frames per second. So the more compute you can spend, the more quality you can get, up to some kind of ceiling where you start trailing off and there are diminishing returns. So you get this kind of curve, in the abstract for any codec standard, but also specifically for every codec implementation. But it's also worth bearing in mind that a particular codec solution will have a sweet spot and will not necessarily cover the full range of this curve. And I think that's particularly the case for RTC. So if you then compare with a legacy codec, the aim is that you are above where that legacy implementation sits across the whole range. And you can see that if you spend lots and lots of CPU and you have very poor FPS, you can get big gains. But the challenge is, can you get those gains across the whole range? So ideally, your next generation solution sits above the curve for your legacy solution the whole way. But given the specialist nature of some of the encoding solutions you have for RTC, this can be quite a challenge. So you're aiming to do two things. Firstly, you're aiming to move your curve above and to the right to get more gain across this range. But you're also trying to improve the total range that you can reasonably cover, where you do get good performance. So it's a double challenge. So given that understanding of performance, what are the difficulties that we face? Well, the major issue in RTC is deadlines. So you have to produce a frame generally every 33 milliseconds, and those frames can vary considerably in complexity. And why do they vary so much in complexity? Well, for modern codecs like AV1, they get their coding gains by having a lot of tools that you can use. And therefore, there is potentially a long tail of tools that you could exploit in order to improve quality. If you don't exploit those tools, then it's easier to hit those deadlines. But you want to exploit those tools to get the gains. So how can you solve this conundrum? So we identified three key areas where you can work on this. The first is through classification, divide and conquer. So if you can characterize the type of content and what is likely to work on these difficult frames, then you can reduce the number of things that you have to test and the amount of work that you have to do in the limited time available. So here you can apply some real intelligence, both in the sense of lightweight AI or ML, but also through more classical arguments for analyzing that content. Then the second thing is, of course, you want to optimize everything in sight. Now that means not just using a lot of SIMD and writing a lot of assembly, but it also means reducing the amount of code size overall and the amount of memory footprint, and having clever algorithms to truncate the amount of work that you have to do in order to get a solution. The final approach is parallelization, and this is where there's another major difference between RTC and other applications. Because you have to operate often with zero latency, you have to do most of your parallelizing, if not all of it, within a frame. And this can mean that you may have hundreds or even thousands of jobs to do if you want to parallelize in order to properly exploit the CPU footprint that you have. And you have to do this with the minimum possible overhead. So you need to manage thousands of tasks, which in frame encoding come with a lot of dependencies, without an excessive amount of overhead in dispatching those tasks to different cores. So this can really help even if you're fast enough to encode in a single-threaded way, because it gives you some safety margin to parallelize if you get something particularly complex coming out of the blue. The second area of challenge is around rate control. And this is also related to this very polarized nature of complexity that I alluded to earlier. Now, one issue here is that quite often when we think about rate control, we think very much in terms of a classical model of a leaky bucket buffer model, where you define an average bit rate or a maximum bit rate, and bits leak out at that rate and you add them to your bucket and so on. But what we find particularly with customers is that they're actually after something more. It's not sufficient just to stay within the parameters of some specific model that they specify. They are often looking for maximum smoothness in the size of your frames, in the rate that you have. So typically, for acceptance purposes, customers will apply sliding windows of different time periods over your bit streams to make sure that things are smooth. And they're doing this because what really causes problems in many RTC applications is sudden changes in bitrate overloading intermediate nodes and causing packet loss. And it's avoiding packet loss that is the objective of a lot of rate control. So for Aurora 1, what we developed was a method of lightweight complexity assessment in order to tackle these issues whilst providing smooth dynamics for the rate control. So this means managing your peak bit rate when something complex arrives and knowing that it's complex when it does arrive, and controlling the maximum frame size so you don't produce a lot of bits onto the wire all at once. Now bear in mind again that we might be doing this with parallelization in place. So we are trying to control the bit rate whilst distributing a lot of work across several cores. This enables us to control the resilience and prevent packet loss downstream of the encoder. And it depends on identifying scene changes and making reasonable adjustments like changing resolution. But in particular, we're doing this in the context of layer management. So often when people are applying scalability, so you are actually trying to hit 2 or 3 bitrate targets simultaneously with perhaps highly variable content and doing this all in parallel. So this is where adaptivity comes in. So AV1 supports a number of adaptive features that are very useful in RTC, but pose challenges, especially in conjunction with rate control. So there's adaptive layering. So in a scalable solution, I'm showing temporal scalability here. You might add or subtract layers to your encoding for different targets. And those have an effect on rate control because you need to control the bit rate for the layers independently, but produce a common total bit rate as well. And then there's adaptive resolution, which allows you to avoid dropping frames, for example, when the bit rate goes down, or increasing quality when bit rate goes up, without having a big keyframe that would cause you resilience problems because you can predict in the normal way. But there are some other cool applications of adaptive resolution. You can, for example, insert keyframes only that are a smaller resolution. And that is one way of avoiding problems when there are scene changes. Now we have to do all of this within tolerances that customers might set for adapting that bit rate when these kind of changes happen. So how did we perform? So here's a couple of examples from live streaming and video calling. So in the live streaming case, I've shown you a portion of a waterfall curve. So the reference here is X264 medium, which sits on the X264 curve. And we can actually get both speed gains and big quality gains. So 48% bitrate reduction in VMAF and 1.6 times the speed of X264. And we can actually get up to twice the speed of X264 if we are prepared to lose a few percent. Then for video calling, we implemented our encoder on the iPhone, on an iPhone 12 in fact, and we found that we could go 40 to 90% faster if we matched video quality, but we were several times faster for screen content while simultaneously giving large bitrate savings, 60% or more. And then we were doing all of this whilst being more than twice as fast as we needed to be for 1080p30 and 720p30 single-threaded, although as I said, you might want to use multiple threads just in case. So I'll leave you with some thoughts about the future of video encoding for RTC. Now, when people talk about the future of video encoding, they typically have this kind of hierarchy in mind with 3 layers. So there's where we are now, where you can accelerate and improve the effects of video encoding for current standards by having AI-empowered encoding and super resolution pre-post processing, that kind of thing. So enhancement technologies applied on top of conventional codec. Then looking forward, there will be new standards. There's the emerging AV2, AVM. There will be the next generation standard from MPEG. And these may or may not include an increasing number of ML tools within them with a conventional architecture. But what people are really excited about is the possibility of whether you can apply a full ML model from autoencoder to video encoding. And I think one key point there that we really need to understand is where would such an encoder fit on the kind of waterfall curve that I've shown you. If the complexity is so high that it will only fit in the bottom right-hand corner, then that will limit its applications. But if we could get a range of complexities out of these technologies and adjustable complexities out of these technologies, then we really have something very powerful. So I think this is where research needs to go to understand how we can have a flexible solution. The second thought I have is that the kind of turbocharged gains that you get from ML right now are very much related to resolution and really the difference between the intrinsic resolution of the video and how many pixels it's actually encoded with. Now, we've had multi-resolution encoding for a long time, scalability and so on. But to really exploit it, you need to have some understanding of how much intrinsic resolution there is and how much you can generate. And so this is a really exciting area where new tools could be involved frame by frame or block by block in emerging standards. So I'll leave you with some takeaways. So if you have a new video codec solution for RTC, it's important that it should have range and flexibility. So it needs to have the features that you want, but it also needs to cover a wide range of operating points so that you can cover as much of your current application as possible and get the gains that you want. Now, it's difficult to get big gains. It involves a lot of engineering, but they are definitely there, and you can get some really significant performance that can take you to the next level in RTC. And finally, we're seeing increasingly that AI is turbocharging encoders, but also within RTC applications. These enhancement technologies are turbocharging the quality that you can get. And moving forward, we will see these technologies getting pulled into the core codec technologies themselves and producing the next generation of video solutions. So that's all I have for you today. Thank you very much.
Thank you, Thomas. Our next session is delivering immersive 360-degree video over 5G networks, and it's presented by Gang Shen. Gang will talk about how 5G and edge computing are transforming immersive media, especially 360-degree videos. He will show us the whole process of making and streaming these videos, from using multiple cameras to sending them over 5G networks, including a look at performance improvements in bandwidth and latency. Gang works for Intel as a system architect and has a lot of experience in media processing and network communications. He has also filed over 20 patents and contributed to several standards for media and communication technologies like MPEG and Dash. Now let's hear from Gang.
Immersive media is one of the killer applications on the internet and telco networks. For example, metaverse, AR, VR, and cloud gaming. It is a known challenge to stream and broadcast immersive media content over public network, especially 5G wireless network, due to the constraints of bandwidth and latency. Hi, my name is Gang Shen. I'm from Intel Network and Edge Group. Today, I will use 360-degree video as an example to analyze the bottlenecks in the technical stack and present our efforts to bring immersive experience to the user. To successfully deliver immersive media over the network, we need technologies from different domains. From the top to the bottom, those technologies can be roughly grouped into 3 layers. Media processing. In this context, it is about compress and organize the media content into a data structure that can be easily transported and accessed through networks. There are existing video codecs that can be used to compress immersive media content like 360-degree video and volumetric data. It is important to note immersive media may need more flexible ways to access partial contents in the 3D space. The media transport, just like other type of data, most video contents today are delivered by TCP, HTTP-based transport protocols. However, HTTP and TCP protocols are rigid in congestion control and packet retransmissions. That could be overhead for immersive media transport because not all contents are equally important. Network infrastructure, it is a fundamental layer for network transports. As we know, even for the 2D video streaming, the network topology where the CDN is located is critical for the transport latencies. Edge server defined by technical industry can intelligently utilize wireless quality of service for media streaming, and it can also greatly reduce the interactive latency by being closer to the client devices. Now, let's take the vertical view and see how to build a holistic solution to deliver 360-degree video broadcasting. 360-degree video is a simple version of VR. The user's viewing perspective is from the center of the sphere looking outward. It supports 3 degrees of freedoms. Users with HMD can look left and right, up and down, and pivot left and right, but they cannot move throughout the virtual space. Each frame for 360-degree video is projected to a 2D rectangular so that it can be compressed by video codecs. Furthermore, sees the content only within the viewport. The viewport-dependent streaming can save a lot of bandwidth. To support this viewport-dependent streaming, the video codecs will need to support tailing to segment the full view content into smaller pieces and packing to pack video content with a lower resolution of the full view. You may find more details about 360-degree video in MPEG-I OMIF standard. With the tailing support in video codec, bitstream rewriting can be used to quickly pack the tails for any new viewports. However, there is still a big challenge during the viewport switch because of the temporal dependency built into video compression. Look at the bottom diagram, which is a sequence of frames in the viewport-dependent streaming. At the beginning, the viewport is at the center of the frames. When the viewport switch happens between the second and the third P frame, the tails in the new viewport in the orange color is not decodable in the receiver devices. In this case, we can only scale up low-resolution tails and make up for that position until the next iframe comes. So in viewport-dependent streaming, MTHQ latency, motion to high-quality latency, is evaluated. The usual MTP motion to photon latency can be satisfied by using the low-resolution content. Then we come to the media transport layer. We can easily find this kind of comparison between RTC and HTTP-based transport in many papers. HTTP-based transport do have advantage in terms of deployment and scalability, but UDP-based RTC protocols, for example RTP, are very good for low latency transport, which is necessary for immersive media. Moreover, it is much easier to extend congestion control algorithms in UDP-based protocols. So RTC is critical for both immersive media and 5G network. Now we select the WebRTC to be the transport for making viewport-dependent streaming and for 360-degree video. In this diagram, we can see there is a constant exchange of viewport information and viewport content between client and the server. The WebRTC client will constantly send the viewport information to the server. The WebRTC server will pack the high-resolution tiles for the given viewport plus the full-view low-resolution content all together into one frame and send it back to the client. Now we have figured out media processing and media transports. Finally, we will deploy this application in certain network infrastructure. There are a few factors to consider when we deploy this application. If we place this application in the cloud, in the data center, the one-way latency is about 100 milliseconds, so the viewport exchange for the 360-degree video will take at minimum 200 milliseconds in the round trip. If we place this application on the on-prem network, we do get much better latency. However, we will get difficulty to scale this application to the large region. So to trade off those factors, then we can select the technical edge as the place to deploy this application. And in the edge server, we can also benefit from the 5G quality of services. To put everything together, we come up with this end-to-end WebRTC-based AK 360-degree video broadcasting solution. In this solution, we separate media functions into three pieces. The media ingestion function and also media distribution function will work with the 5G UPF, the user plan function, that reset in the edge servers and co-locate with 5G RAN. The media ingestion function will handle multiple camera inputs and provide 360 video stitching and encoding. Media distribution function will handle viewport packing and viewport switch based on each client's feedback. There is a media control function in the middle. It will provide signaling and orchestrations for different devices, including camera and receiver devices, to join the broadcasting. Media control functions can be placed on the public network. Here comes the demo video. In this demo, we have two 360-degree camera and three Android phones as a receiver. First, we place one camera in a remote room. In the server room, we have 5G core 5G RAN plus all the three media functions as we defined in the previous slide. On the receiver side, as we can see, we have three Android phones. On the right, the two Android phones receive the content from the camera, the first camera in the other room. And also we have another camera in this room just for the end-to-end testing. So the Android phone on the left is receiving the content from the camera on this table. And on the back of the room, there is a 5G transmitter to support the wireless connection. Okay, based on the implementation and the measurement, we got significant good results. For the glass-to-glass latency, we achieved 1.3 seconds And in the comparable HTTP-based solution, usually that will take more than 5 seconds. The media processing during the entire pipeline takes about 0.9 seconds. So we can achieve much better latency by improve this media processing using hardware acceleration. The MTHQ latency is the second latency we measured in this implementation. The MTHQ latency is the viewport switch latency, and is in this implementation we have 200 milliseconds, which is way better than the comparable CDN and HTTP-based solutions. In the latency breakdown, we can see the media processing is still the largest bottleneck. The temporal dependency, the gulp size in the codec will cause about 40% of this interactive latency. We had new solutions to reduce this MTHQ latency. We designed a new coding structure based on scalable video coding to remove the gulp size, the gulp structure completely from this interactive latency. Secondly, we used time series analysis to predict the next viewport so that we can prepare the contents in advance. Our solution is one of the prototypes in the ecosystem. There are many significant developments in recent years. With regards to media processing, new video codecs, AV1, VVC, start to consider immersive media contents that are beyond traditional 2D videos. 3D volumetric codecs like WebRTC, GPCC are coming to the market as well. As for media transports, new transport protocols, QUIC and HTTP3, are tailored for media streaming. Especially L4S provides a new mechanism of congestion control, which can significantly reduce end-to-end latency. In the infrastructure layer, the telco industry has defined XRM, extended reality services. Like what we have seen in the demo, the immersive media engine and services now can be running in the user plan of a 5G mobile core to achieve low latency. And this model also supports the device and wearables less expensive or with preserved batteries. In addition, in this model, the network layer can be aware of the importance and the correlations of video packets so that it can give much more efficient traffic handling. All of this will pave the way to reduce the end-to-end latency and improve visual quality for the immersive media over the 5G network. Now let's summarize today's presentation. Large-scale immersive media broadcasting is possible with today's network capability of 5G and edge computing. Media processing performance is still the bottleneck for the user experience. To create truly immersive experience, collaborative cross-layer innovation are expected. In this implementation, we identified key building blocks and demonstrate a scalable RTC as a service for immersive media applications. In the future, we plan to support more immersive media data formats and to incorporate new technologies from different domains, especially network AI and media AI, to accelerate the delivery of immersive media over 5G network. Thank you. This is my contact information.
Thank you, Gang. Up next, we have the privilege of hearing from Fengdang Liu and Fan Zhu, two accomplished software engineers at Meta, who will share their work to improve network resiliency using long-term reference and read Solomon code. Fengdang with his extensive experience in RTC network resilience, has been at the forefront of Meta's efforts to reduce media latency and enhance quality, ensuring that communication remains uninterrupted across the globe. Alongside him, Fan Zhu brings a wealth of knowledge from his work on improving media quality in video calling applications, focusing on innovative solutions in bandwidth estimation, video scaling, and optimizing large group calls. This presentation will be followed by a live Q&A session moderated by Jia Dong. So don't forget to submit your questions on the AtScale conference website's live stream chat. Now let's hear from Fengdan and Fan.
Video calling brings people together despite their geographic distance. As our product scales for more people around the world, packet loss emerges as a major challenge, which not only causes video freeze, but more importantly, it undermines user experience. In the context of RTC, packet loss recovery should not only occur in the real time, but also occupies as little traffic as possible. So in this talk, we'll take a deep dive into our secret sauce to deliver a low latency, low freeze RTC video experience. We will first describe an industry baseline, which is available in open source. Then we will take a step further, describe our unique solutions using the most recent codecs and error correction technologies, which are long-term reference and Ray-Solomon code for error correction. First, let's talk about the baselines. In the open source community, there are three mature solutions: retransmission, keyframe, and XOR-based FEC. They can be grouped into two categories: reactive or proactive. Retransmission and keyframes, they are reactive. For example, if receiver side detects a sequence number gap, it will send the RTCP NAC request to the sender side, so that sender can resend those lost packets so that receiver can resume the video playout. As you can see, because sender only needs to retransmit those lost packets, it takes as little overhead as possible. So retransmission is low overhead, but the whole process takes a whole round trip time, which has high latency. But there's another case. Under bursty loss, number of lost packets could be huge. Also, the retransmission itself could be lost as well. So that could accumulate the length of the NAC list. In that scenario, if we insist retransmitting everything with retransmission, the network actually will be overloaded. In that case, usually what we do is for sender side to send a keyframe to refresh the whole video decoding chain. However, there's a catch for the keyframe. Keyframe is large, but that may be fine because we have pacer, but more importantly, keyframe has low quality. The image is flaky. Okay, so we are done with the reactive mechanism. Let's move on to the proactive one. There's actually only one proactive mechanism to recover the lost packet, which is forward error correction, or we can just call it FEC. So as an open source solution, XOR-based FEC is available in WebRTC in form of Flex or ULP. They work similar, but the high-level idea is that the sender proactively sends those redundant information, right? And so that on the receiver side, whenever a packet loss event occurs, the recovery can happen in real time. But as you can see, it takes a lot of traffic. So in production, it's not very rare for us to take half of the overall traffic for FEC, which could have been allocated for much better video quality. So before we dive into the details of LTR and RS code, let's have a high-level overview of how they step in our whole NR mechanism to improve the whole system. First, keyframe. Just as a recap, keyframe is huge, and it has poor quality. So LTR can not only reduce the overhead, but also presents much better image quality. On the other hand, because open source community only has XOR-based FEC as its solution. As a result, RS code is really needed because RS code can actually take less overhead, but achieve much better recovery property. We will come back to that later. Next, I'll hand it over to my colleague Fan to talk about LTR.
Hi, hello. My name is Fan, and I'm going to talk about a long-term reference frame, or LTR. So I'm going to first talk about what is LTR. So as we know, videos consist of two types of frames. One is key frame, which has large size and is self-decodable. Another type is P frame, which has much less size, but usually requires reference frame in order for it to be decoded. So as a result, we can see the chain dependency of the video frames. So now assuming there's some packet loss in the frame 5, which is a type of P frame. And as a result, due to the chain dependency, the receiver not only cannot decode frame 5, but also it cannot decode all the frames after frame 5. And that's going to cause video freeze. So in this case, the receiver either has to request the sender to transmit all the medium packets, or it has to ask the sender to send another keyframe. And as we know, that both solutions are not very ideal. So here's another idea. Sender can periodically mark in some frames as long-term reference frame, or LTR. In this case, the frame 3 is marked as LTR. So after the receiver got frame 3, it can save its frame 3 in decoder buffer. And once there's a video freeze, the receiver can ask the sender for encoding another P frame using the frame 3 as a reference. And as we know, since the receiver has already got frame 3 and saved its decoder buffer, then after got a frame 7 into case, it can decode it without any issue. So we call frame 7 LTRP because the type of P frame which uses a long-term reference frame. And after receiver got frame 7, it can decode frame 7 and all the following up frames, and hence solve the video freeze issues. So that is LTR. But why do we want it? As Feng also talked about before, so compared with keyframe, it has advantage of having less size and high quality, because after all, it's kind of P frame. And compared with ENAC, it can be more efficient, especially in high lossy network. Because instead of requesting sender to transmit up to 20 packets, now receiver only need to request an LTRP. That's why we believe LTR has the potential to become a foundation block for better loss recovery approach. Because instead of requesting ENAC or keyframe, now we can request an LTRP. Now let's look at the overall flow of the LTR. It's pretty straightforward. On the sender side, most of the work is done in encoder. So encoder just need to periodically generate some LTR. And after each LTR is generated, it will be assigned a unique ID. After receiver got the LTR, it needs to send acknowledgement to tell sender which LTR it has received. We choose to use RDP head extension for acknowledgement, which means that each acknowledgement will be sent out in the outgoing video packets. And when the video freeze happens, the receiver can send RTP message to the sender, ask the sender to generate an LTRP. And the sender will start encoding a P frame using the latest long-term reference frame the receiver has acknowledged. So after the receiver got this LTRP, it can continue decoding. So while the overall flow looks very straightforward, it turns out we actually have to make sure every detail is correct to make sure the whole flow works flawlessly. Otherwise, it is very easy to see video corruption and video freeze. Here I provide you an example where we see the frame 195 is a LTRP because it refers to the 191 instead of 194. But instead of decoding it correctly, we can see this frame is actually corrupted. And that's usually caused by referring to the wrong reference frame. So it turns out to solve the challenge, we have to make sure to take up two things. First is that we have to uniquely identify each LTR frame. So that's particularly challenging because we have both software and hardware encoder. And those two encoders generate different types of LTR tokens. So to deal with this issue, we actually designed a unified API that translates them into a counter with slice head pattern. This counter is large enough, so it will not wrap around easily. And also, from receiver's perspective, it will only see one type of the long-term reference frame IDs generated by both software and hardware encoder. And the second challenge is that we have to be careful with the reference frame management. Because previously, we act every LTR once we receive every packet for the LTR. But we found that later, this LTR might not be decoded. It will be dropped before being decoded. So as a result, the receiver will not save this LTR in its buffer. So in future, once the receiver got an LTRP encoded using this LTR as a reference, the receiver is unable to decode it, hence cause a long freeze. That's why we have to make sure to check the reference frame and make sure it exists before the frame to encoder, before sending the frame to decoder. We did some performance analysis on the LTR compared with keyframe. And here, this figure demonstrates the advantage of the LTRP compared with the keyframe in terms of video quality. So the y-axis here shows you the PSNR, which is the indication of the video quality. As we can see, that LTRP achieves higher PSNR compared with keyframe. And also, it achieves high quality while maintaining much less size. As you can see, that LTRP compared to keyframe at low bandwidth conditions, its size is almost 8 times less than the keyframe. So we implement the LTR and launch LTR on Messenger, and we replace the keyframe with the LTRP under 2 scenarios. The first scenario is high loss conditions, which means that the receiver needs to request retransmission of up to 10 missing packets. Second scenario is that frame buffer timeout, which means that the receiver cannot decoding any frame for longer than 1 second. Previously, we just request keyframe in the case, but after replacing those keyframe requests with LTRP, as expected, we see significant reduction in the number of keyframes. For example, we see the keyframe numbers drop by 37% in high loss conditions. And also we want to mention, this reduction is done without any trade-off in the video freeze. In fact, we can even observe almost a 0.76 reduction in the video freeze, which is caused by less congestion due to the less size of LTRP. Okay, that's the end of my part. Now I'm going to transition to Fengden.
Let's talk about how our XOR-based FEC works in the production. FEC is not free. As a matter of fact, it's quite expensive. It takes bandwidth from the regular video traffic, which could have been allocated for better video quality. In production, generally, FEC takes more traffic as RTT, PLR, and overall bitrate grows. So the production pattern is actually very flexible. FEC could protect the packets within the same frame or across different frames. But there's a trade-off. As you protect across different frames, the recovery rate will increase. However, there will come with a natural delay because the FEC packets needs to wait for more frames arrival before being able to decode any lost packet. There's another important area is that the performance of XOR-based FEC degenerates fastly as the size of the encoding group grows. This is exactly where RS code steps in. WebRTC has a matured implementation for XOR-based FEC, such as Flex FEC and URP FEC. They work similarly. For example, if we want to protect 4 source packets with 3 priority packets, after looking up the table, here's the protection schema. Recovery is only possible if only 1 packet is lost in the protection group. For example, in this protection schema, priority packet 2 is protecting S1, S3, and S4. If both S1 and S3 are lost, S4 cannot be recovered at all. So let's take a step further to see where XOR-based FEC really falls short. With the same schema, on the receiver side, we have S4 where S1 to 3 are lost. In the meanwhile, we also have 3 priority packets. Because all of the packets from S1 to S3 are lost, there's no way to recover any of the information even though we have 3 priority packets. Alternatively, if those priority packets were generated by RS code, every lost packet could be recovered. In fact, regardless the number of source packets, if we generate K packets by resiliency code, it will allow us to recover up to K lost packets in any manner of combination. Here's an overview of how resiliency code FEC works. On the sender side, we have all those source packets, and depending on some mechanism, we decide how many priority packets to generate. So we feed all those source packets into the generator matrix, and the generator matrix can give us as many as priority packets we want. Afterwards, we send everything over the network. On the receiver side, if there's some packet loss for the source group, no problem. We just need to figure out how many source packets are lost and see if there are enough priority packets to recover the lost packets. Just to recap, if there are X lost packets in source packet, as long as the number of priority packets is not less than X, we can have 100% recovery. So after we arranging arranging the source packet and parity packets in the correct order, we fed them into the decoding matrix. And afterwards, we have a working video flow. As for now, Resume Code FEC is available in every Messenger RTC course. And in this year, we are expanding the coverage to Instagram video course. You may wonder, how can you integrate the RS Code technology into your own video FEC stack? And here's our tips. First of all, WebRTC provides a very good implementation of XOR-based FEC, whose pipeline can be referenced in integrating your own RS Code solution. Furthermore, codecs is the key. There are tons of different implementations for RS Code, and among them, there are different trade-offs within each implementation. So you need to decide the right config so that you make the right CPU and memory trade-offs in your own application. Furthermore, in low bandwidth condition, the size of FEC packet per overhead matters, because Resume Code needs some extra information for receiver to take so that it can recover the lost packet. However, those extra information are not free. You need to convey them in the header. If the header takes too much bandwidth, it will actually regress the network condition in an undesired way. As a result, you need to design a scalable format so that it's not only has small overhead, but also works with other technologies like temporal layer. Last but not least, maybe it's a surprise, but RS Code is not always better. In some scenario, especially when the bandwidth is not super high, XOR-based FEC can do partial recovery, whereas RS Code cannot. So you need to come from your own use case and design a combination of smart algorithms to maximize the benefit of RS Code. Next, I will hand it over to Fan for our final summary and future plans.
Okay, now I'm going to talk about conclusion and our future work. As we reflect our journey to enhance video stream quality in loss environments, we are really encouraged by the effectiveness of the strategies we have implemented. First, let's talk about LTR. We have to mention that LTR is not a silver bullet. At some conditions, its coding efficiency is sometimes the same equal with a keyframes, especially when the distance between LTR and LTRP is large enough, which means we have carefully designed strategies to the frequency to send LTR and also the frequency to request LTRP to make sure we do not really negatively affect the user experiences at some conditions. But we can see that with careful design of the reference frame management mechanism, LTR can achieve the same efficiency in reducing the video freeze compared with the keyframe. And that's really encouraging because that LTR achieves this same efficiency with less size and even higher quality. And now looking at Xcode, in fact, launching Xcode can already reduce the video freeze for up to 2 to 3% for Messenger. It means that Xcode does effectively recover some bursty losses that cannot be covered by XOR FEC before. And we have mentioned that we just launched Xcode broadly, but we can actually explore some of the special optimization for the HD video, in which case we expect that Xcode can achieve even higher video freeze gain compared with the baseline of XOR FEC. Looking into the future, there are a lot of exciting work ahead of us. For example, we definitely want to expand the LTR coverage. Currently, we only implement LTR in Messenger when the software encoder is used. In the future, we want to actually expand the coverage to other codecs as well, such as AV1 and our hardware encoder. That's going to broaden our impact across various platforms at Meta. Second, we want to design intelligent loss recovery mechanism. Now we have different weapons to combat video freeze in lossy network. We have FEC, we have LTR, keyframe, and retransmission. Now challenging is that how to smartly choose which one to use under different network scenarios so that we can maximize their capability to reduce video freeze. That's going to be interesting and challenging problem we want to tackle next. And finally, Meta is committing to contribute to the WebRTC community. For example, we're actively working on contribute our group FEC implementation to the upstream WebRTC. And after that's done, other players in the industry can leverage our solutions to reduce freeze and help them scale better in the group call scenarios. Okay, thank you for attending our talk. Please let us know if you have any questions.
Hello, everyone. I hope you've just enjoyed the wonderful talks covering various aspects of RTC video. Now, we are very happy to have all our speakers, Xiang, Thomas, Gan, Fengden, and Fan, join us live for the Q&A session to share their thoughts, experiences, and insights with us. My name is Ji Dang. I'm a software engineer with the video calling team here at Meta. I work on video call quality measurement and improvement across Meta's RTC products like Messenger, Instagram, and WhatsApp. And it's my pleasure today to moderate this Q&A session. Now I've seen the questions coming in, and we'll do our best to answer as many of them as possible. So let's get started. Xiang, I would like to start with you. Do you leverage SVC capabilities for AV1 in order to support relay architecture?
Oh, yeah, that's a great question. So the way we started was majority of our calls are one-on-one or peer-to-peer calls. They still go through relay server. So some of the SVC capabilities, they are more applicable for large group calls or group calls. Definitely like the simulcast will be applicable there. But temporal layer is something that we leverage even for peer-to-peer. And we are running experiments on that right now. So we are using some features like RPR of AV1 for peer-to-peer calls. And we are running active test on temporal layer, which we have been using in previous codecs with AV1. And in future, when we expand it to group calls, then we will be leveraging the features like simulcast and more advanced features.
Yeah, that's another question for you, Xiang. How do you switch codecs on the fly without interruption to playback? What challenges did you face while implementing this?
Yeah, another great question. So the good thing is we have been using SDP as a signaling for negotiating the codecs, and it allows us to negotiate multiple codecs upfront. So for example, between all the participants, we can negotiate all the capable codecs and then find the intersection. In past, we have also been able to switch the codecs when some participant joins who is not able to support, let's say, a participant joins from a very old app version, which does not have the latest codec support. So in a normal case, we are able to negotiate, let's say, H.264, AV1, VP8, all the codecs at the beginning, at the call setup phase. And then during the runtime, we detect based on bit rates or CPU usage, the sender can make a decision to switch the codec from 264 to AV1 without any negotiation. The decision is on each frame basis. It does mean like the sender has to encode a new keyframe because it's a switch of the codec and start a new codec, which is same as any resolution changes, which we do for sender when the bitrate changes. And the same thing on the receiver side, the codec type or the payload type identifies what codec is associated with. And the receiver is able to detect that the input RTV packets have a change in the payload type, and they are able to instantiate the different codec and decode it. So what we measured was for the end users, it looks seamless. There is no glitch, there is no big pause. But still, like there is hundreds of milliseconds of glitches in some cases, depending on the jitter buffer and network sizes or the network conditions. But mostly it's seamless, like almost not visible to the end users.
Thanks, Xiang. So now I have a question related to the long-term reference frame. Does this repair scheme scale to middle boxes and relays for large SFU-based multi-party calls? It seems like that instead of placing the burden on relay node NAC buffers, the burden has to go back to the original sender to generate these LTR keyframes. Fan, would you like to share your thoughts on this?
Sure, that's a great question. So in fact, our current approach only works for the P2P immediate pass. So we're expecting to adding the support to the group call, the effort will be non-trivial. So first of all, it is true that this burden cannot be put on the relays, and the request has to go to the source, which actually have the buffer of the long-term reference frames, so that can generate LTRP based on the buffer of the LTR frames. So second of all, on the receiver side, so imagine in a large group call, it might receive the multiple streams, right, from all the other senders. In that case, when it only has one outgoing stream, then it need to acknowledge the LTR sent from like multiple streams. That is non-trivial. So that's why we haven't really considered expanding this to the large group call yet.
Thanks, Van. Here's another question for you. We configure video encoders to have a certain number of reference pictures. LTR may focus us to increase this number. This in turn would impact the encoder and decoder complexity in this shortcoming?
That's definitely a great question. So as a matter of fact, we don't really adding a lot of actual long-term, a lot of frames. So for example, the OpenX264 it only use at most one long-term reference frames. So which means that no matter how many long-term reference frames you might generate, so it will only generating the LTRP based on the most recent act LTR frames. The similar thing also applies to the hardware encoder as well. So as far as we know, the iOS hardware encoder only also can support at most 4 long-term reference frames, and also it can only use the latest acknowledged one to generate LTRP. So it doesn't really add a lot of complexity to the encoder and decoder design here.
Thanks, Fan. Now I have a question related to AV1 encoder. What do you think is the limit of performance for AV1 in RTC, especially at lower complexity? Thomas, would you like to share your thoughts on this one?
Oh, that's quite a hard one. I think it depends a lot on where you sit on the complexity spectrum. So on the complexity side, you can think of AV1 as a kind of superset of VP9 and a VP8. So you kind of know a priori that you can match the complexity and performance of those prior codecs. Most people don't write an encoder to do that, but it does mean that you should have confidence that you can do that. You can adjust your encoding algorithm to at least match the performance of prior codecs. But the more wiggle room you have, the more CPU you have, the more you can get coding gains out of that. So what's challenging in writing an encoder is not necessarily supporting very low complexity. It's supporting a big range of complexities. So it's possible to get very significant gains, as I hope I showed in the talk. But when you have a codec, an encoder that's capable of supporting these very high performance operating points, there can be a lot of overhead in your encoder in order to reach those lower complexity operating points. So you have to write things in a kind of scalable way to do that. So in quality terms, I think I've really been surprised at how much extra gain we've managed to get in recent years, both in the open source codecs and in our own. Really, there's a lot of mileage, and I'm excited by the possibilities of using really clever pre-analysis with increasing use of ML techniques. So I think the sky is the limit, really. There's a lot of mileage still to go, even in low complexity RTC encoding.
Thank you, Thomas. Great. Yeah, I personally also thought about a similar question, whether we can use the AV1 as H.264 if we trim the AV1 heavily enough. Appreciate your insights. So we have question. The next question is about the 360-degree video. So Gang, this question is for you. Why choose software video codecs when processing 8K 360 video?
Yeah, so that is the implementation decision, and at the moment we have this set up this implementation. Not a lot hardware codecs support AK transcoding. The second factor is about this tailing and piping during the 360 video processing. So it is very important to have this the random access, especially on this 360 video encoding, so that we can quickly switch the viewport. So that kind of feature is supported in the HEVC MCTS, the motion constraint tail side. That is, however, that is not a kind of, it is just an extension of the HEVC standards. So it's not widely implemented in the hardware HEVC encoder. So that is the reason, finally, we can select the software HEVC encoder support the MCTS. Then we make this choice for the 360 video encoding. Certainly, if for now we have quite a lot of tools in AV1 and also VVC, so it's likely to have a much better hardware acceleration for the AK 360-degree video encoding.
Thanks, Gang. Now I have another question related to long-term reference frame. Looks like the long-term reference frame is really popular topic. So, Fan, the quality of long-term reference frame depends on video content. For high motion content, the quality and the required rate of LTR could be worse than keyframe. Do you consider this to request LTR?
Yeah, that's a great point. So, in fact, as a matter of fact, the quality of LTIP highly depends on a lot of factors, such as video content and also the difference between the LTIP and its reference frame. As mentioned in this question here, so if there's a lot of, for example, motion in the video content and the difference between the LTIP and its reference frame is large enough, then in some cases we observe that most of the LTIP consists of only like eye blocks, which means there's not much difference between the quality size of LTIP and the keyframe. So we definitely will consider do some optimization here. So for example, we observe that we are aware that there's a mechanism to detecting the difference between the frame and its reference frame in the OpenH264. So definitely one optimization we can make is that if the difference is large enough, then we consider instead of generating another LTIP, we can fall back to a keyframe in that case.
Thanks, Fan. Yeah, LDR does not come for free, but we need more thoughts to handle them carefully. Fengden, here's a question for you. Is it possible for FEC layer to provide more bits for key LTR frames and less bits for rest of the frames to save bandwidth?
Yes, this is what's being done as part of WebRTC solution. It gives more traffic to protect keyframes, and we are adding support to give the more traffic to LTR frames, even for retransmission data as well. That turns out to be very useful.
Thanks, Fengden. Here's a question for the BWE part. For the higher bit rate, why did you have to make changes for the BWE that comes with the WebRTC?
Okay, yeah, I think so. The default bandwidth estimation and the Google congestion control that ships with WebRTC does an extremely good job for most of the use cases for our RTC, right? But when it comes to really increasing the bit rates and pushing the networks to the limits, there is scope for improvements. And BWE is still an area which is still evolving, right? There is no fixed algorithm or a single algorithm which is considered as an industry standard or this is like solved problem. So this is where most products they differentiate. And to some extent, the design of algorithm depends on several factors like what scenarios your product supports, what your customer base is, in what conditions they operate, and what you are trying to optimize for. Is it for the video quality, audio quality, or enterprise or consumer? So this is an area where most products innovate and differentiate. So every product has their own secret sauce, and this is what we also did. And the analogy I would make is the algorithm works for a certain conditions, but when you increase the bit rates, you have to keep evolving it. So for example, consider, let's say you are building a car, right? And you have a really good engine. Now you can easily press the gas and accelerator to go to the higher speeds, but you can't simply keep on increasing the speeds or engine unless you keep evolving, like let's say the tires and the brakes to be able to handle the congestions on the road or slippery conditions. So you have to keep evolving both how you push the network limits or how you increase the video quality and bandwidth, and also keep evolving your bandwidth estimation and congestion detection algorithms to avoid those really bad congestions and call drops.
Yeah, interesting. The speeding could be terribly dangerous without the premium tires and brakes. Again, let's look at another long-term reference frame. Is there a way for Pacer to control the number of frames between keyframes? Fan, please.
Yeah, we actually don't control that from Pacer. So there are a number of other ways we can control when do we want to send keyframes, right? So for example, we used to have a control on the encoder side that generated keyframes regularly, maybe something around every 2 seconds. But we found that it doesn't really bring any benefit. Right? It doesn't really bring benefit as keyframe usually have large size and less quality than ordinary keyframe. So as of now, we don't really sending proactive keyframes, and all keyframes are sending on demand way, right? So for example, we have to return change. In that case, we have to send a keyframe. Or when the decoder is getting blocked, then the decoder needs to request a keyframe to have a fresh start. So now, yeah, we have way to control when do we send a keyframe, but we don't send a proactive keyframe and proactive keyframe, and we don't control that in Pacer.
Thanks, Fan. So now I see a question regarding the screen content for the AV1, which I am personally very interested in it. So AV1 seems to give really good results for screen content. What's the reason for that? Are there types of content that are especially challenging? Thomas, would you like to address this one?
Yeah, I mean, that's a really good question. I think people have alluded to that, the fact that AV1 has got screen content tools in the main profile, and that's obviously really useful, but actually that's only part of the story. When you're targeting an encoder on screen content, the content itself behaves differently to camera content. So being able to deploy those tools with encoder algorithms that understand the statistics of how those frames and, for example, scrolling video and the kind of content that you have with Word documents, Excel spreadsheets, web pages, that kind of thing. That's also really important. So you've got to have an optimized encoding path for it as well, and put the two together. What's really challenging in RTC is when you have mixture of content where there's very different statistics put together. So if you think of an example of sharing a web page with embedded videos in that web page, so you're scrolling up and down and videos are playing inside that web page, that can be particularly difficult because you're trying to optimize for motion in some parts of it and optimize for screen content in the other. So that's something that I've spent some time on in my life, doing that kind of thing.
Thank you, Thomas, for sharing your insights on the screen content coding tools. So there's another question from the audience. what's the most challenging part to build an end-to-end XR application? Gang, would you like to share your insights on this one?
Yeah, I think this to build an end-to-end solution, we often need this kind of cross-domain collaborations. So basically, you need components from the media industry and also from the network industry and from the technical wireless industry. So what we kind of experienced is in each industry, they are quite many valuable and legacy technologies. But very often we see those innovations from one industry may not be quickly adopted by another industry. So that makes this kind of coordinated evolution very difficult. For example, the video codecs AV1, it is if we want to really kind of promote the AV1 codec in the telco industry, that takes quite a long time to do that. The second thing is about the interoperability. So basically, if we want to have an end-to-end solution, we had to consider the device and also the users across regions. So that means many components and technology need to be standardized and synchronized.
Thanks, Gang. So we are close to the end of the Q&A session, and we have time for 2 more questions. So Fengdeng, here's a question for you. What causes the extra FEC header overhead for read Solomon code when compared to XOR FEC?
Sure. So the RS code decode requires the encoding group information to get the correct decoding matrix. Versus in XOR FEC, you just need to know what are the packets that used to protect, that used to generate this FEC packets, and then you just need to grab this FEC packets and fill the gap for the lost packet. So that creates a little bit more overhead for RS code payload header.
Thanks, Fengdeng. So the last question, that's end the session by the long-term reference frame. Fan, so the question is, from which codecs are you seeing the improvement by using the long-term reference frame other than H.264? Also, is Meta team planning to make upstream contribution of long-term reference frame to the WebRTC community?
Yeah, that's a great question. So as of now, we are only applying it to H.264, both software and hardware. So we have already shipped this long-term reference frame on the software encoder across the messaging app. But as far as I know, the WhatsApp team is also successfully applying the LTR to VP8 as well. And as for the contribution, yes, we are definitely we are actively considering doing that. So as a matter of fact, we've already started some discussion with upstream and other company on how the upstream part of the design in the upstream community.
Thanks, Van. So, well, it is toward the end of the session, and there are still questions from the audience we're not able to cover here, but we will make sure that questions are all answered offline. Again, I would like to thank all our speakers for the great talks and taking the time to share their experiences with us. And I also want to thank our audience for their interesting and engaging questions. Thanks, everyone, and see you after the break.
That was another fantastic Q&A session. Huge thanks for all the engaging and thoughtful questions. We'll now take a quick break. See you back shortly. Welcome back. We are about to start our last session for the day. Tzachi Levent-Levi from Blog Geek will be talking about the past and future of WebRTC 2024 edition. WebRTC is going through some changes with different players contributing to its codebase. In this session, we'll look at who is working on WebRTC and what they are focusing on. This will help us understand where WebRTC is headed and how it might change real-time communication. Tzachi has over 20 years of experience in the area of software and communications. He is a developer, entrepreneur, and consultant in the area of digital communication. I first met him a few years back when he invited me to give a talk in one of the Cranky Geek RTC events about calling products in Meta. Now I am honored to have him with us today to share his insights on WebRTC. Let's get started.
WebRTC has been with us for over 10 years now, and it's time to look at the past of WebRTC and see where we're headed in the future. This is a 2024 edition of the past and future of WebRTC. To start off, let's understand what WebRTC really is. And for me, WebRTC is roughly 13 years old. You know, depending when you start looking at it, 2011, 2012, it's quite old now. It's an open standard, which means that there is a specification somewhere you can go and read and then implement that. The standard specification was written by the W3C and the IETF. On the other hand, WebRTC is also a permissive open source implementation where developers can go, download the source code, make it their own, and build their own application and deliver it, no matter if it runs in the browser or not. At the end of the day, WebRTC is also a Google project. They are the ones in charge of the open source implementation. Remember that, because this is going to be something critical moving forward. So for me, WebRTC is all of the above. If you look at the eras of WebRTC, we started in 2011. That was the age of exploration. The question we've asked ourselves when we wanted to use it was, should I be even using it? Is that good enough for me? You know, it's available only in Chrome and Firefox. That's not enough. Maybe there is some other technology to use instead of that. After that period came the period of growth, 2015 to 2019. At that time, the question we asked ourselves was, how do I use it? How do I build applications with it? What is the right approach? The reason for that was that Edge and Safari came and used WebRTC as well. There was no longer a question of should I use that? Is this a technology that is here to stay? The immediate answer was, yes, it's here to stay. Now we need to figure out how to build something with it. Fast forward to today, 2020 and beyond, we are in the age of differentiation. The question we ask ourselves is, how do I compete with all of the other companies that are building voice and video applications? The thing that marks this differentiation era are, first of all, version 1.0 of WebRTC. We finally have a specification that is standardized. Before that, it was a draft. We've seen Zoom rise through the pandemic, and we've seen billions of people indoctrinated of how to use video conferencing. And today, we also have AI, generative AI, and LLMs, all the technologies of machine learning. How does WebRTC fit into all of these? The age of differentiation. If you try and look at WebRTC from the prism of usage, you can look at the Chrome statistics of the calls to, let's say, get user media, one of the APIs that are marking the use of WebRTC, me opening up access to the camera or the microphone. And you see the increase in the number of pages that open in Chrome that use get user media. So throughout the pandemic, 2020, 2021, 2022, you see this huge peak in use and rise of WebRTC. Almost a 4-time growth throughout this time that was kept even after the pandemic. And the question to ask is this going to stay with us after the pandemic and beyond 2024? Okay, are we going to stay with the same level, go high, or go lower than that? My name is Tzachi Levent-Levi of Blog Geek Me. If you ask me what I am, I'm a developer by heart. I've been developing since the age of 13. I haven't written a line of code probably in the last 10 years or so, but I still identify as a developer. I have been dealing with voice over IP since 1998, also video conferencing, and I've become a consultant and analyst in digital communication, mainly because of WebRTC. I am the past co-founder and CEO of TestRTC, a company that provides services for testing and monitoring WebRTC applications. It got acquired by Ciara, and now I'm a senior product manager there, dealing with TestRTC. Why is all that important? I've had the chance to talk to a lot of developers throughout these 20 years of my career on voice over IP, video conferencing, and the last 10 years around WebRTC. And what I've seen is that at the end of the day, WebRTC is a kind of a three-legged stool. On one leg of the stool, you have the browsers. If you want to build an application, you need to make sure that it runs with the browsers. Okay? Whatever implementation exists there is an implementation that you need to be able to support. The second leg of the stool is the developer ecosystem. This one is built on the fact that there is a lot of developers using WebRTC through the open source implementations, commercial implementations, applications, managed services. There's a plethora of solutions out there built on developers. The third leg of the stool is the important one for us today to gauge the future of WebRTC, and that's libWebRTC. libWebRTC is the permissive open source implementation by Google. It is the one that is embedded and available inside Chrome, but also in all other browsers, Edge, Firefox, and Safari. It's also the one that is embedded in a lot of native applications out there. A lot of the mobile applications that do video conferencing today are built on top of libWebRTC. Developers that took libWebRTC, downloaded it, and used it inside their applications. This is how important libWebRTC is to the ecosystem and the future of WebRTC. It is why we need to go and dive deeper into where libWebRTC is and why. So the first thing to look at is the release cadence of WebRTC. libWebRTC gets updated roughly once a month, along with Chromium and Chrome. Chrome has a release once a month, hence libWebRTC has a release once a month at the same time. Every 30, 40, 50 days, you'll see a new release coming out based on the release cadence of Chrome. This means two things to me. The first one, there are many small frequent updates that happen. Each one of them in libWebRTC will add a new feature, change a behavior, optimize something, polish something, but they're going to be small in their nature. Nothing big that changes between one release to another. The second thing is that, like everything with Google, we're going to break things and then move along. Because we have the liberty of all of these small releases, we move really, really fast, and we have a lot of capabilities of changing things and trialing stuff and seeing what works and what doesn't. The problem with that is that we as developers need to follow through with that release cadence and the fact that things are going to break for us. Another way to look at WebRTC is the contributions to libWebRTC. Each year in this graph, you see a bar that shows the number of commits that were done into the libWebRTC project. If on top of that you place a graph that we've seen of the use of WebRTC inside browsers, how people end up using WebRTC, you see something really interesting. The moment that after the peak of WebRTC and the commits are going down, the number of contributions going down, there is this peak that comes with the pandemic. It is as if we're investing less in WebRTC in the moment that we need it most. And for me, that means one thing. libWebRTC has switched and shifted into maintenance mode. Google has not decided that they're not going to invest in communications. It's just that they're investing elsewhere within that food chain of communication. They're doing a lot of things outside of libWebRTC, where in the past they've done them inside libWebRTC. They are themselves in the age of differentiation, trying to differentiate their products from others using WebRTC. The second thing to note here is the different colors. Each bar has two colors to it. The green one is the Google employees that have committed to libWebRTC. And then the blue one is external committers. What does that tell us? That libWebRTC is Google owned. There are not many external contributors to libWebRTC. At the end of the day, it is an open source project, but it is owned, maintained, managed, and its future is based on whatever Google decides. This brings immediately two insights. The first one, if you're a developer, you need to be as close as possible to Google's own plans and requirements. Okay, whatever Google is doing, the closer you are to that, the easier your life is going to be. Going off the reservation means that the source code of WebRTC might not be there with you. Bear that in mind. The second thing is that if you're building native applications, then you're on your own. The whole build system for WebRTC, the whole implementation, the decisions that were done, the configuration that goes into the native applications is something that Google is investing a lot less in than they are doing for the browser. So you need to take that into account and to deal with all of the updates and changes that you will need to do in LibWebRTC to make your native application better. So LibWebRTC is where we need to look at. And LibWebRTC itself has three focus areas if you look at the last year and what is being done today by Google within the source code. These areas are externalize, collaborate, and optimize. We're going to look at all three of them and understand where we're headed with WebRTC. The first one is externalize. We talked about the age of differentiation, and now it comes through the great unbundling of WebRTC, something that Google hinted in 2019 and we now see happening full throttle. These are technologies like WebAssembly, insertable streams, web codecs, and web transport that are changing the way people use WebRTC or decide to use something else. To understand how these work, let's start by looking at the processing pipeline that happens inside WebRTC. We've got a camera and a microphone. We want to actually communicate with someone else. So I need to take the data from the camera and microphone, capture that, then encode it. Encoding means taking the raw data, compressing it before sending it. So after I compress it or after I encode it into something manageable, I'm going to send that off through the network. The receiver end is going to receive the data, decode it, open it up, and then play it back to the display and the speakers. This is the processing pipeline of WebRTC. It's more complicated than that, but this is like the main concept of it. What are we going to do to unbundle it or to make things more flexible for developers? The first one is in the introduction of a feature called insertable streams. What we're going to do is we're going to let developers go and put their own code in JavaScript in the browser between the encoder and the sender and between the receiver and the decoder. We're going to let developers add encryption, add markers, add metadata before this is being sent over the network. So while WebRTC is looked at as a monolith implementation, we're now adding flexibility using that. After doing that, breakout boxes were added. These are insertable media streams. This allows us to take the data captured, so the actual frames from the camera, and change them. I can blur my background or remove it. I can add a silly hat on my head or do various other things that I want to, like maybe add text over here or whatever, and do that inside the video itself, either before encoding and sending it, or after receiving it, decoding it, and before playing it back to the user. So breakout boxes and insertable streams enable us a lot more flexibility. This wasn't enough. So what we did next was say, you know what? Let's take the send and the receive part and take them out of WebRTC altogether. Let's create this new standard inside the web browser called Web Transport, which will let us do things that we can do with WebRTC, just without WebRTC altogether. So now I'm letting developers build their own transport protocols without using WebRTC with its own transport protocols to build something slightly different. So if I'm fine with a little higher latencies, but better quality and reliability, I can now do that by doing something else and not use WebRTC. If I want to compete with others and do something with Web Transport and not WebRTC, I can attempt to do that. Last but not least is Web Codecs that was added, which allows me now to take the codecs, audio and video codecs, and do frame-by-frame encoding and decoding inside the browser, things that weren't possible before and aren't possible with WebRTC either. All of these capabilities are new. They don't work in all browsers today, and when they do, they're still not that stable, but this is where the future is, and it's going to mean that Some of the use cases that we've used to use WebRTC for are going to switch and be used by web transport and web codecs. Let's move on from externalize to collaborate. Collaboration for me is screen sharing. First thing that comes to mind with screen sharing is, well, full screen sharing. I'm going to take the whole video that I have, the whole screen that I have, and share that with someone else. This is how we did screen sharing in the past. After that, we said, well, you know what, privacy, let's just share one window of our screen, not the whole thing. And from there, we said, well, you know, it's a browser. Why not share just one tab out of the browser? And we're trying to even make that the default or the most easiest thing to share. This is where we are today with collaboration. You can either share the full screen, the window, or the tab. What happens now is that we're trying to add more granular bits and pieces of sharing and collaboration. So next in line is region capture. I'm going to take a bit of the screen, okay, just a piece of that web page. I'm going to crop that area and share that area as is. So if I'm doing that and there is a menu going down in there, that's going to be inside that cropped area. It's still good because I can now put that region and put the videos next to it without sharing them inside the same window. What we're going to see coming into the browser now is a solution of element capture. What we're going to do is we're going to be able to tell the browser to share us from a page only a specific element of that page. An element is a DOM element, which is an HTML piece that is being rendered by the browser before displaying it. It's part of the page, not all of the page. There are things that can be in the foreground, you know, in front of it, that are not going to appear inside that element that is being captured and shared. This makes for a better collaboration experience and a smoother run, especially if you're thinking about the fact that I am collaborating in one application, a window from another application. How do I do that in a way that I don't need to jump from one application to another? Now, to answer that question even better, we have a new feature that is coming called Captured Surface Control. So I'm sharing something, but I just want to scroll it down or to the side or zoom in and out. I can now do that with WebRTC without switching to the other page back and forth, to the other browser tab. And this is coming to Chrome in Chrome 123, I think. It begs the question though, if we're gone through full screen window, browser, region, element, and now surface controls, what else can we do? What comes next after that? Are we going to allow people to click in a meeting inside a different browser tab or use the button clicks to control other things? What does that say about privacy and security? These are questions that are not answered yet, and it will be interesting to see where this is headed. That was collaborate. Last but not least is optimize. For me, optimize is two things. The first one is house cleaning. We have technical debt we need to deal with. We want to optimize the code, make it faster, better, easier to debug and to maintain. These are things that we're going to do anyway. And these happen in WebRTC and libWebRTC all the time. The other thing is the more interesting ones. And this is the fact that we start seeing new codecs coming into WebRTC, new ways to compress and to encode the data that we have for audio and video. This comes in the form of two codecs, AV1 for video and Lyra for voice. Let's start with AV1. If you want to think about AV1, for me, this is how I look at it. AV1 is a new codec, so if I could do something with VP8, VP9, or H.264 in the past for WebRTC in a certain amount of bitrate, I can reach the same level of quality with a lower bitrate using AV1. Okay, so I can save on bitrate and gain the same quality. Now I can up the quality now by using the same bitrate. So I can get better quality for the same bitrate that I used in the past. The downside of that is that AV1 is processing hungry. It takes up a lot of CPU and a lot of memory, more than VP8 and VP9. So if we're aiming higher in quality, we need to have better CPUs, and we don't have them yet, not all of us. So where you see the focus today is in reducing the bit rates while maintaining quality. Okay, where does that leave us? The focus areas today in AV1 is in the low-hanging fruit. The first one is going to be screen sharing. we've got large resolution, but small frame rate, because it's just screen sharing. And interestingly enough, within AV1, text looks a lot better than it does with other codecs. So using lower bit rates makes sense here while maintaining higher quality. The other one, obvious, is low bit rates. If I have a lower bit rate in my network, poor connection, lower resolutions for the videos that I'm sending because of the use case, I can make use of AV1 today. Why? Because if the bitrate is lower, I don't need as much CPU as I need for the higher bitrates. So I can sacrifice more CPU for WebRTC and AV1 than I would in the higher bitrates, because I have that available. The third thing is interesting. We now have multi-codec simulcast coming up. Up until today, if you wanted to use simulcast, it was using only a single codec. Simulcast means that I'm going to send multiple bitrates of the same video. So I'm sending multiple bitrates. The media server is going to pick and choose which of these bitrates, which of these streams it is going to send to the participants in the conversation. Why? Depending on whatever he sees fit, based on their bitrate, CPU, layout of the screen that they see, whatever. Multi-codec simulcast means that now I can take the lower bitrate stream, use that with AV1, and the higher bitrate streams, and use with them VP8 or VP9. So I can make use of AV1 within large conferences to get higher quality for the lowest bitrate available, which is interesting. The last one was hardware acceleration. We're simply sitting and waiting to see what happens with hardware acceleration. Other than AV1, we have Lyra. Lyra comes to do voice. It is an AI-based codec, which means very low bitrate, and doing very good job in trying to understand what people were saying and predicting that. This is the AI part of the Lyra codec. The interesting piece, though, is that Lyra is an external codec to WebRTC. It's not part of the WebRTC source code. What happens today is that we have a WebAssembly implementation of Lyra available, and people have taken that implementation and wired it into WebRTC using web audio, insertable streams, or web audio and data channels. Unlike other codecs, Lyra also have competitors. There is Microsoft Satin, Cisco has their own codec, Dolby has their own codec. These codecs can be stitched in the same way through WebAssembly in order to support these solutions in WebRTC. And what happens next is the big question. Are we going to see Lyra squeeze into libWebRTC as another codec implemented? Is it going to be added as part of the Opus codec? Opus includes already two codecs, so a third one, it's not that hard. Or are we going to see it stay externally and people, developers using it externally to WebRTC and stitching it into their application? This is a part of differentiation through unbundling. So we've talked about libWebRTC. We've seen how important it is to us and what the future holds for libWebRTC. And the question that remains is, how is this going to change the use of WebRTC by our users? Is it going to go up, go down, or stay roughly the same at 4 times the use? And we see these competing roles or competing ways of this happening. We've got web transport and web codecs that are unbundling WebRTC, and are taking away some of the use cases from WebRTC, allowing us and developers to implement it using other means, which means we're going to see a reduction in the use of WebRTC. But we also see technologies like insertable streams and WebAssembly that allows us to do more with WebRTC, to increase our flexibility and to increase the level of user experience at the end of the day, which again will entice developers and then users to use WebRTC, which means that we're going to see it growing. My hunch is that we're going to be at roughly the same way for this year as well, at 4 times what we've seen before the pandemic, and that means that the competition is here to stay, and you need to differentiate your applications from others in order to win. Thank you for being with me.
Thank you, Tzachi. Next, we will transition to another vital aspect of real-time communications, RTC observability. Our next presenters, Mandeep Diol and Ishan Kot, will guide us through the problem of observability in RTC applications, a cornerstone for operational monitoring and debugging at scale. Their talk will not only cover the broad scope of observability, but will also introduce us to Rator, which is a real-time data aggregation service designed for Meta's RTC applications. Please welcome Mandeep and Ishan.
Welcome everyone to the talk on RTC observability. I'm Ishan. I'm a software engineering manager supporting the observability team at Meta. And I also have with me my colleague Mandeep Deol, who is a software engineer on the same team. Together, we are going to talk on RTC observability. What is this area all about? What are the various challenges in it? What are the novel solutions that we came up with? And the future scope that lies ahead. So before we begin, let me answer the simple question, what does observability even mean? Well, simply put, observability is a measure of how well you understand the underlying system. Now here at Meta, we like to divide this area into various themes that help us to prioritize and organize efforts in each of those themes. So the first theme is platformization. RTC at Meta is not just a service for one product, but a platform that serves many different products. So platformization helps us make sure that we build generic solutions that scale across all the wide variety of products that RTC support and work in various different conditions, such as low bandwidth or constrained devices, as well as high-end enterprise scenarios. The second theme is privacy. Privacy is at the core of every product that we build at Meta. Whenever we upload any user data, we always need to make sure that it does not violate any user expectations. At the same time, any engineer that accesses that data only does so with the proper business need and in order to improve our products. That is what we tackle in the theme for privacy. Now, there are two more themes, reliability and efficiency, that are very closely tied to each other. Reliability makes sure that all logs that are uploaded are reliably uploaded and are present wherever engineers expect them to be. Whereas in efficiency, we make sure that we get maximum value out of any log we upload. This is because any log we upload has a cost associated with it. In terms of the client CPU that it takes to compute this log, the client bandwidth that is needed to upload this, which can also interfere with the calling performance. But even on the server side, there are costs related to storage and CPU. So there's a very tricky balance to strike between reliability and efficiency. And the final and most challenging theme around observability is call debugging. This is where we dive deep into particular calls and try to analyze them. So this is the focus of our talk, and we'll talk in more detail around the challenges in call debugging, the novel solutions that we came up in this space, particularly related to real-time log aggregation, and the future scope in observability area. Now, as we talk about call debugging, all of us always had that one instance of a bug that was really hard to repro, and we couldn't even understand how the system got into this place. So that is the challenge in call debugging. But there are broadly two major challenges. One use case is when we want to analyze a lot of calls in aggregate. This is really useful for analyzing trends or reacting to user behavior. There are a lot of proprietary tools already existing that are able to effectively solve this problem by building tables that log all of the data related to a call and then creating visualizations around them. However, there is another big challenge in call debugging. And this is when we need to dive deep into a particular call to analyze all of its data in detail and find out some edge case scenario or issue that is really hard to debug. So for this particular challenge, we built a proprietary tool called CallDive. And as the name suggests, it enables you to dive deep into a particular call. This collects data from all the participants in that call and provides a lot of visualization tools depending on the structure of the logs that we collect. Each log has a different structure, Some are better visualized as a time series format, whereas some are better visualized as histograms or bar charts. And this is what CallDive enables us to do. It allows us to slice and dice the data in order to quickly find where the problem might be and fix it. This is a tool that is loved by all engineers across Meta. However, you might be thinking, how did we come up with this tool? And what are all the challenges that we faced along the way? And most importantly, is this really the most optimal solution that allows us to effectively scale call debugging to all our products? And how do we uplevel the observability area from here? So to talk about all of the challenges and how we came up with this tool, I'll pass it off to my colleague Mandeep, who will dive deep into the technical challenges.
Thanks, Ishan, for that wonderful introduction. I'm Mandeep Vyol, and we're going to explore the call debugging space a bit more here, look at all the challenges we encountered while developing this tooling. So, let's get into it. All of the tooling that we have here at Meta in this particular space is backed by our common logging infrastructure. So let's look at that and understand that better to get a feel for the initial challenges that we had. All of the clients and the servers on a particular call are generating different types of logs, and all of these logs first make their way to Scribe, which is our distributed event streaming system. And from there, they can be streamed into different backends depending on the use case. So for example, they can go into our backends for our real-time data analysis tools that enable, trends analysis that Ishan talked about, or they can go into Hive, which is our data warehouse, and from there they can be read by tools like CallDive, or at least the initial version of CallDive. I should also point out here that there's a one-to-one mapping between a log and a table. A log entry is a row in one of these backend tables, and a field is a column. So this is the initial sort of common infrastructure. Let's now look at what the challenges were here. So before I even get into like the problems with the initial version of CallDive or some of our real-time data analysis tools, I should mention that before any of this existed, engineers were just using Hive, the data warehouse. So in order to debug a particular call, they would have to make, dozens of SQL queries, fetch the data for individual logs, and then piece it all together themselves. And they had no support for any custom visualizations, like for any specialized data that we had. So that's sort of where the idea of CallDive came in, and some bright engineer put together a tool which can read all the logs for you without having to write any SQL. You can click on it, get special visualizations. But that initial version still had some problems. One of the problems was that the log availability delay. So logs can take hours to land in Hive because Hive is not designed for this particular use case. So engineers would, after an issue was reported, engineers would have to wait hours before they can actually start debugging and deep diving into that issue. Additionally, a single request to fetch one of these logs from Hive can have like a P90 latency in order of minutes. And so when you're making dozens of these requests to do the initial page load, you're almost certain to hit one of these, the P90 latencies, and have the page load take over like a minute. So that was a really frustrating thing for our engineers to deal with as well. And some of the real-time data analysis tooling that we have has the limitation that they don't support joins. So if you wanted to do any type of analysis that between multiple tables or multiple log types, you're kind of out of luck there. So those are the problems. Like, what did we do about these things? So the first thing we noticed was that the key issue here in both of these domains was the segregation of logs. And this is an inherent problem in this space. It's sort of the nature of RTC systems. They're distributed. So what we decided to do was build a system called Ralligator, short for real-time log aggregation, to resolve these issues. Let's take a look at how Ralligator works and where it fits in. This is a high-level view of Ralligator. So of course, we didn't want to go and change all of the existing infrastructure and we wanted to leverage whatever common infrastructure we had as much as possible. So Ralligator fits in right behind Scribe. So it's just another consumer, and it can read data from Scribe, and it can generate aggregated outputs for both call dive and our real-time data analysis tooling. So what do I mean by aggregated output? For the real-time data analysis tooling, the aggregated output is just another new log. And it's a concatenation of all the input logs that we have, the separate segregated logs we have. And all of the fields in those become fields in this new log. In addition to this, we also have facilities for being able to add some custom fields. So you can write some logic and compute some values and add additional fields here as well. And that gets written out to Scribe and can be processed by our real-time data analysis tooling. So effectively performing a join. For call dive, we take the list of all the logs belonging to a call and write it in a single file to Manifold, our cloud storage system, and call dive can fetch it from there with just one request. Now let's sort of dive a little bit deeper into the Ralligator architecture. Ralligator could be thought of as having 4 different components, or being made up of 4 different components. The first is Scribe Manager, which is responsible for managing, reading all of the data from all of the different loggers into the system. And then we have a call index, which is an in-memory key value store, where the keys are the call identifiers and the values are a list of all the logs belonging to that particular call. Then, of course, we have the metrics component, which is responsible for generating the aggregated log output and computing any custom fields that we want to compute. In addition to that, we have call completion, and this component is responsible for determining when enough logs or when all of the logs for a particular call have arrived so that the call can be processed. Another way of thinking about the system is that there are 2 sides to it. There's an input side and there's an output side. The input side is basically pulling data from Scribe and putting it into the call index. And then we have the output side, which is running on a timer. So the call completion logic is running on a timer and trying to determine, hey, like which calls have now received all of the data, and then writing out the aggregated outputs. Most of the components are fairly straightforward and simple to understand. One of the big challenges here is call completion. So you may have noticed that we're keeping all of the data for all of the ongoing calls that are in process in memory. So if the input rate ever exceeds the output rate for any significant amount of time, we risk running out of memory. This is why call completion is very, very important. And it has an incentive to try to complete calls as quickly as possible. So, we can complete calls and flush out the data from memory as soon as possible. But this is in conflict with our other requirement. We want the aggregated outputs to be as complete as possible. So if for some reason, if we complete calls too quickly, we risk not getting all of the logs for a particular call. And there's actually no deterministic way of knowing when all of the logs for a call have arrived. In particular, this is mainly due to reliability, in particular, like client-side logging reliability. Client-side logging, it has to play nice with the apps it lives in. There are certain restrictions for when logs can be uploaded, if at all. There are like bandwidth restrictions on, at which time on which networks, under which network conditions the logs can be uploaded. So the call completion is mainly a heuristic, and it works based off of server-side logging, which is reliable. So we wait for the end call server-side log, and then we have certain timeouts to wait for client-side logging. And if we exceed certain timeouts, we just flush the call at that time. These timeouts are based on like measured latencies that we have captured in production. This is very challenging and slightly tricky to get right, but we've managed to get it right, and it works fairly well in practice. Some of the additional design notes on Ralligator: of course, we're dealing with tons of data. we're processing millions of calls a day. We can't run on a single machine. So sharding is involved. Managing multiple machines is a challenge. Running the system across multiple machines is a challenge. And getting the write and the read side to agree on a sharding strategy can be complicated. In addition, currently we don't do any sort of replication or backfill in the system because mainly we're concerned about debugging use cases, and there hasn't been a real need to do this. But the data is available in Scribe for multiple days, so we can build a backfilling solution cost effectively if necessary. Many of the times when we describe the design of Ralligator, the question we get asked is, hey, why not use external distributed key value store, something like Amazon's DynamoDB? The simple reason there is that it's not cost effective just because of the amount of data we're dealing with, and it has its own sort of replication cost related to it. So when we did our initial estimates, this cost was like almost an order of magnitude. So with that, you're up to date with the current state of things in this particular space. And now I'm going to hand it off to Ishan to talk about some of the future innovations that we're looking at.
Thank you so much, Mandeep, for that great technical overview on call dive and how we deal with call debugging. Now that we know all about that, let's think about the future. Where do we take it from here, and where are there more opportunities in like the whole observability space? So we already saw how amazing a tool call dive is, but that is barely scratching the surface of it. There's much more we can do there. We not only can add more custom visualizations for all of the different types of logs, but we are also starting to ingest more and more product logs into call dive, and each logs from every different product has its own structure and visualization. This is starting to evolve call dive as a platform to serve more and more use cases. On top of that, we are also starting to enable real-time debugging in call dive. Today, all of the logs are uploaded when the call ends. However, logs can be continuously streamed and visualized. This enables us to debug a call live while it is ongoing, and we can even fix problems and improve the quality of the call on the fly. Now, apart from just call debugging, there's various amounts of challenges in scalability. Video calling is now evolving beyond traditional audio and video to also serve other scenarios such as metaverse. These scenarios are much more complex and lead to a lot of logs being generated. This makes it very difficult to analyze all of these logs and also to handle them through memory constraint that we have within systems such as like Ralligator. So that is another challenge, and calling is also becoming more private. And we want to give users full control over the data that they upload and how it gets used and processed. So this is another big challenge in the privacy area. Finally, now let me talk about what's on top of all of our minds, and which is artificial intelligence. There has been so much advancement in this field, and we believe that observability is the perfect space where we can use all of these techniques. We already know that Ralligator is capable of producing metrics that power top lines for RTC. On top of it, we can even introduce metrics based off of machine learning models that can quickly classify calls with certain problems such as no audio issues or no video issues. This can help us quickly stay on top of these problems and fix all of these issues, and also capture user sentiment through these ML derived metrics. Apart from that, we can also use advanced techniques such as generative AI to analyze all of the different logs that get collected. And then debugging can be as simple as just starting a conversation with an AI to ask questions like, did the server process video frames correctly for this call? Did participant X receive the audio in this call? And then you can even come up with various theories for what might have gone wrong in the call and check them with an AI. So we feel that the future in this space is like really exciting, and I can't wait to see how we will tackle all of these challenges in the future. So now that all of you know about the entire observability space, I'm sure that when building RTC applications, you will prioritize this area highly, same as we prioritize media quality and other features. Please feel free to reach out to us if you have any questions for us, and thanks so much for joining us on this journey. Thank you.
Thank you, Mandeep and Ishan. Up next is Open Source from One to at Scale with Sean Dubois from LiveKit. Sean will explore the highs of creating impactful projects, the lows of common pitfalls, and the wins of effective open source practices. Having founded Pion WebRTC and contributed to many other projects, Sean brings a wealth of experience and a deep passion for free and open software. This session will show us how powerful open source can be if we use it the right way. It will give us useful information that will help users, developers, and companies. Take it away, Sean.
Open source, from one to at scale. So originally, when I thought about doing this talk, I thought the thing that people wanted to hear about most was a niche WebRTC topic from implementing Pion. You hear about like, here's the battles of implementing DTLS. But really, what people are most interested in was my experience with RTC and open source and what I learned along the way and the benefits of it, and like, why do I keep doing it? You know, why am I not just worried about working on a proprietary product full time? So for me, I break down the reasons I do open source into two categories, or these are the things that I've realized or why I continue to do open source. Is first off, for me, I just build better. I feel that the things I do are higher quality. I enjoy it more, and that's why I continue to do it. And the first thing is that I spend a lot less time debugging issues. Where when I'm at a company and I'm debugging an issue that's particular to the company, it's frustrating. You do it alone. You ask for help, but sometimes everyone else is busy. But the thing with open source is you're not alone anymore. You're not, and we'll talk more about this. The other great thing about open source is I don't question what people want anymore. There's direct communication. I can figure out what you care about. And then the last thing is when I'm building, now it's much easier to find people to help me to build because I have a resource that I can pull directly from. And the other part that keeps me involved is that I feel like I just live better as a developer. There were always things when I was at a job that I wanted to try, but I couldn't find time to, but now I can. My career became something entirely different when I started working on open source. I had more opportunities and I had more people and more companies I worked with. And the last thing is I find myself not as frustrated with the software I use anymore. So before I go into talk all this, I want to give my background so you can understand where I'm coming from. A lot of these things that I care about are heavily biased because they were solutions to problems that I had. So my background is that I created on Pion, which is a collection of Go software that's worked for RTC. The most popular one is the WebRTC implementation. You see it. A lot of companies use it. It's used as a component for a lot of open source projects. And then after I wrote Pion, when I was on paternity leave, I wrote WebRTC for the Curious, which was a book about how WebRTC actually works. And now that that was all done, recently I've been involved on adding WebRTC to OBS. So instead of broadcasting via RTMP, now you can broadcast via WebRTC. And then full-time I work as the field CTO at LiveKit. And beyond that, before that, I had experience in a lot of different places with WebRTC. And that's the reason I'm so excited about this field, is that it lets me do so many different things. I've got to see people do robotics. I've got to see people do broadcasting. And now I'm seeing people do AI with it. Like, not all of these things I wasn't an expert in, but I get to be on the periphery and help people with their WebRTC problems. And that's why I continue to be excited and invigorated about this field. So thank you to everyone. First off, as I give this talk, I'm going to talk about a lot of different open source projects, and it's going to sound like, oh, Sean is the person that built all this by himself. But the truth is that there were so many people that helped me, and I want to thank everyone. This list is everyone that's been involved with WebRTC for the Curious and Pion. Thank you so much for contributing and working with me. These projects wouldn't be what they are today without your help. So I'm lucky. I get to come up here and talk about it and be excited, but only because of everything that people did here. So first up, I want to talk as a company, why should you be excited about WebRTC, or why is it something that would be beneficial to you? So the first lesson for me, or one of the things that really convinced me that WebRTC was worth my time at a company, was working on Kinesis video streams, which is a product at AWS. And we did a pure C implementation of WebRTC because we had all of these products that wanted to do real-time video. You had security robots and delivery and, just all these things that were outside that usual space that I was used to of conferencing and broadcast. But the issue was they couldn't use any WebRTC implementations that existed at the time. The requirement was that they needed a WebRTC implementation that was in pure C because they were using proprietary tool chains, and it had to be very, very small, under 256 kilobytes. And at that time, this AWS was already very familiar with GitHub. And so by default, we were putting stuff up on GitHub. We wanted to be developer friendly. I understood this. I wanted to use CMake and GitHub. But one of the things that happened that I was so excited about is for the first time I got to talk directly with customers. There was no more guessing about what did they actually want? What should we build? What should we be doing? But now these developers would get on GitHub and they would file issues directly and be like, I'm trying to build this and it doesn't work because of this reason. And we would talk back and forth, and maybe sometimes they'd even open PRs, which is amazing that you would build something and then someone would come and correct your mistake. And at the same time, they're still paying for the product. It's just a better experience for everyone. That developer isn't blocked on you. The developer outside the company isn't blocked on you anymore. And so here's a screenshot of one scenario I had where Uber was using KVS. Alex reported the issue and he ended up fixing himself. It's such a great experience as a company to not have to block others and just have them see them be effective without you. The next time that I was working on open source that I really started to understand it and fall in love with it was when I was using GStreamer as a library. So my involvement with GStreamer was pretty minor. I added AV1 support and small bug fixes to RTMP source and other things like that. But I had run into this very deep seg fault in the video compositor, completely out of my realm. I was debugging all of this, tens of thousands of lines of C code. I was completely lost. And so what I did when I got started is I just posted a GST launch of the issue. And surprisingly, another developer contributed the fix. This is something that I would estimate would take me 4 to 6 weeks. Not something I could fix on my own very easily. And after that 4 to 6 weeks, I probably would have come up with a worse fix. But for me, it was so relieving to not have to deal with this issue and on top of that, all these other people that were running the issue as well, it was fixed for them. So when I see companies that they believe that if they work in a silo, they want to keep all of their information proprietary to their company. They want to just work on internal bug trackers and not have to worry about talking with other people. You're not actually saving yourself time. Having outside people get involved, and maybe I see a lot of people, they believe that open source will slow them down, but I don't believe that's true. That you're actually slowing yourself down, working in this silo and just talking among yourselves. That if you have these outside eyes and help, you'll actually move much quicker. And the next is I see, and it's kind of a similar problem, but the same core issue is that people believe that working in that silo. So I worked on Amazon Silk, which is a Chromium fork just for the Silk browser and other devices by Amazon. And we had hundreds of patches that were just specific to these devices. And some were adding Amazon features, so they couldn't be open source, but a lot of it, I believe, would have been useful to send upstream. But it was such a hard process to do that it ended up just being easier to keep things internal. But the issue was we had to employ a team of 6 people that would constantly what we call up-leveling, which is just rebasing the master branch of Chromium to make sure that we were never more than 14 days behind because of security issues and the browser space is moving so rapidly. But when we would rebase, all of a sudden, a patch wouldn't apply anymore. So we would have to go and figure out what was the original purpose of this patch. Many times the original author was gone, so you couldn't even ask them what the purpose was anymore. So we'd wonder, can we delete it? And if we couldn't, maybe we wouldn't even be able to modify Chromium anymore to do this. So my belief is these patches were a liability. They weren't even helping us. That in the short term, it was great to get that feature out the door, but in the long term, it slowed us down. What else could we have accomplished in the time that we spent working on these patches? It might feel that it's benefiting you, that you're using an open source project and you have all these patches internally. Like maybe it feels like a competitive advantage, or it feels like it would be a waste of time to upstream them, but it's just not the case. You're wasting so much time in the short term that the benefits are, I think, speak for themselves. And then next, as a developer, open source has all these benefits. So for me, I started my career in tech. Growing up in Ohio, I had no connection to the tech scene. I didn't understand open source. I didn't understand any of these things. And I loved computers. I loved fiddling with things. I would build, Doom wads. Like, this was my background. But I just couldn't find my start. I would go and buy books at Barnes & Nobles to try to figure out languages, and always ended up as a dead end. But for me, I took a job. I was working in IT. I was installing computers and pulling wires and stuff like that. And they used free PBX. And so I was able to build little small features like making some UI changes or making some small behavior changes to free PBX. And thanks to this, I have my career today. Once I got some knowledge with free PBX, I was able to get a referral into another company, and then I worked full-time as a free PBX developer. And only because of open source do I do any of this work I do today. And now this is what I use to hire other people. So in all these open source projects, I watch out for people that are motivated and excited, and I try to bring them in. As a hiring manager, if your projects were open source, you would have all of these new people that you would be introduced to that you'd be able to hire and work on projects. The next problem is it's just slower to work alone. The first time I saw this was working on the PHP project. So I've been working on open source for a few years. I hadn't done much. I'd worked a lot on company projects, but I hadn't done much outside of that. And so as my first stab, I got involved with PHP, and there was an RFC that I saw that I thought was interesting. And I asked, could I help? And the original author had said, sure, and added me. And I was amazed at how welcome I was, and I was able to bring new ideas, and I learned along the way, and we were able to split the work. And I've kind of brought this into my other projects as well, that the more people you bring from the outside, the more diverse opinions you get about how the software should work. And you would think that would be frustrating. You would think that, okay, you want to just have a singular vision about your open source project, and you don't care what other people have to say. You know how you want to build it. But when you bring other people in, the work goes faster, and these ideas that they bring to the project make it so much better. And as a developer, the other thing that's really important is to realize that you don't even understand the reward yet that working on these open source projects will bring you. So when I started working on Pion, I had no idea where it would take me. I thought it would just be another thing that I work on. I would have fun. I would learn. I would build a couple of things, and maybe I'd be able to use it. My biggest goal is to be able to use it at a job. And beyond that, I had no higher aspirations. But it has given me so much more. The only reason I'm here today is because I started working on that. I was able to travel. I went to London and went to ComCon, and I met all these other people that were passionate about WebRTC and open source, and it just fills me with so much joy and energy. These are finally to find people that care about the same things as me. And my work is more interesting. What I alluded to earlier with working on robotics and working with AI, all these things that I would never be able to see, but because I worked on Pion, that I got to see all these things. And for me, I say yes to every opportunity. That yes, you might not make money directly with open source, but don't let that scare you away. That's not the experiences, and the other things you get will be worth way more than the money you would directly earn. And the last part is about what, as a user of open source, what benefits does that bring you? So one project that I worked on is OBS that I talked about earlier. And for me, I really thought that WebRTC would bring a bunch of benefits to the broadcasting space, to be able to talk to people interactively. Right now when you do RTMP, your audience will type something and then you'll respond to it 3 to 5 seconds later. But with WebRTC, if someone sends a message and I can respond in 200 milliseconds, it's just an entirely different experience. The other one I'm really excited about is this better screen sharing or camera quality. A lot of people will be like, I'm not happy with WebRTC because of the picture quality. But with OBS, I can pick the encoders I use, I can lay out my screen exactly how I want it, and I can broadcast. I think this is the next step in making sure that people have the best experience possible when making content on the internet. And there's other really interesting things like adverse networks. Instead of like blocking and waiting until the network is better, we can do forward error correction or other interesting things. I don't know where this is going to go, but it does feel compelling. But as a user of open source, OBS, I feel very empowered by it. The fact that I can make these changes myself, the fact that I can distribute patches and other people can apply them and use them. Like, it doesn't matter what the owners of the project feel, but as an open source project, I can do whatever I want with it. And this applies to all open source projects, that you can make it into what you want it to be. The other open source project that I learned a lot from was WebRTC for the Curious. So WebRTC for the Curious is an open source book on how WebRTC actually works. The protocols, not just here's a tutorial on how to use Pion. And I did it when I was on paternity leave. I wanted to write down what I learned about WebRTC for the protocol. And along the way, I met so many developers that were doing interesting things, So this was before KBS. So this was my first foray into like talking to people that were doing embedded and talking to people that were doing robotics and talking to people that were doing drones with WebRTC. And I was like, this is wild. I didn't realize that all the interesting things that people could build. And I started to get an appreciation that like one piece of software isn't the answer to all the problems. Not everyone is, some people are doing servers, some people are doing little small embedded things. There's too many constraints. You can't just have one piece of software for everything. So that's my journey as like an individual in open source, all the things I learned and saw and worked on. And now I'm doing something a little bit differently. And I say open source at scale, but it's open source as a full-time job. So right now I'm working at LiveKit, and LiveKit is a pure Go implementation of WebRTC server, and it comes with that batteries added. So you have like SDKs and protocol bridging and all these things that people are building from scratch. And that open source version is also hostable. So you can take that and you can put it and you can pay us and we'll run it for you. And it's been a joy to watch how LiveKit thrived from open source. So for years, I've been watching it from the outside, and this is the things I've been seeing are the things for me that I felt good about joining. So LiveKit encourages the autonomy of people. If you have a bug or you have something you want to understand how it really works, I can just go to GitHub, I can pull down the code for the LiveKit SFU, and I can look how it really works. There's no more just like filing a support ticket and like hoping for the best. I can modify the code and I can support myself. And I love the independence. There's no like vendor lock-in here, where if you're using like what happened with Twilio, where if someone shuts down the WebRTC offering, like you might have a year to switch somewhere else, and like you would build into their proprietary APIs. I like that the users aren't locked in. They can do what's best for themselves. And I love the communication. The fact that I can just be on Slack and people can email me directly, and I don't have to be cryptic about what I'm working on. I'm making PRs on GitHub. If you want to know what I'm working on, you can just go look at my GitHub profile at LiveKit. You don't have to guess what the next things we're going to work on. But one thing I was concerned was about this mix of open source and money. I read about all these companies that are relicensing, and I was like, am I going to kind of fall into the same trap on a personal level now that WebRTC isn't a hobby anymore? There's going to be this conflict of interest. Well, the pressures of work impact the quality. Now that we have to ship something for Q1 so we can do this, will this change? With Pion, I was always able to work at the pace that worked best for me. But at the end, like, I was willing to take that because it's a dream of many to have to work on your passion, which is what Pion is for me. So far I feel good about it. Someone told me, like, as long as you align your incentives with your customers, that things will turn out good. So that's what I'm trying to do. Figure out, like, if I make it so that, things are open source and customers are successful, that if those things align, then I'm doing what's right. And I think in ways, the one I'm really excited about is how LiveKit bills for bandwidth instead of time. So instead of billing N cents an hour, we bill for N cents gigabyte. And that's one of those things where the incentives line up, because I see it's pushing all these users to use VP9 instead of H.264. So yeah, I'll continue to look for small wins like that, where I can do things in a way that, yes, there's financial transactions, but in the way that they're working, it's pushing for what the users are best. And it's not binary. It's with code, you can write a linter, you can write a pre-commit hook to make sure that things work. But with every customer conversation, you have to make sure that you're pushing what's best for people. And it's kind of all this with open source and people making money. People are trying to relicense projects. People are trying to release they have a product where they have an open source version that isn't as featureful. They have a proprietary version that's more featureful. I don't know what the answer is, but it's just something you have to think about in every decision and every conversation. And so that's it. I think for me, this is the multitude of why open source is better. For users, it respects you. It lets you do what's best for you. If the code is open, I can go make the changes. I can build. I understand what I want best. And so I can go and make those changes. As a developer, you represent yourself with open source. There's no more just saying, I worked at this company, and so this is why you should hire me. Your resume can just have a link to your GitHub, and people can see exactly what you work on. And for companies, it's great. It's just a better product that you end up with. And you can hire people better, and you spend less time on things that aren't important, like having a bunch of patches and changes that really aren't that beneficial. And it's really easy to get started with open source. It's not like you have to open source your entire code base. You can just, the next project you work on, consider does this have to be an internal utility, or could this just be an open source thing? Because think of how good it would be for the developers working at your company if they can work on something and they can be more motivated and excited, and people can see what they're working on and it's beneficial for them. Start doing a little bit and see where it gets you. If you want a community to talk about, please reach out. Here's all the ways you can reach me. My favorite place to talk is in the Pion Slack. When you join, you don't have to talk about Pion. Anything video RTC is totally on topic. So join and we'd love to talk. And then if you want to talk directly, you feel free to just add me on LinkedIn and let's talk directly. Send me an email. If you have any questions about open source or WebRTC, I'm always here. Thank you so much.
Thank you, Sean. Let's move on to our final talk of the day and explore how machine learning is being leveraged to solve networking problems with Lian Liu and Santosh Sanderajan. They will be talking about innovative machine learning-based solutions to refine congestion control and bandwidth estimation, enhancing performance by addressing the challenges holistically. Lian's background is in ML for networking, and Santosh's expertise is in solving networking problems. They will share their insights into improving RTC through machine learning, showcasing their approaches and future plans. Following this, we'll have our final live Q&A with speakers moderated by Pavel Punsky. So don't forget to submit your questions on the AtScale conference website's live stream chat. Now please welcome Lian and Santosh.
Welcome to our talk on ML-based bandwidth estimation and congestion control for RTC. I'm Santosh Sundarajan. I'm a tech lead at Meta for ML networking projects. I'll be co-presenting this talk with Lian, an ML lead for ML networking projects at Meta. In this talk, we will talk in detail about how we achieved quality and reliability gains using ML-based solution by targeting different network types. Back in 2021, we rolled out sensor bandwidth estimation improvements with quality gains for high bandwidth network. But we saw reliability regressions in low bandwidth networks. Similarly, in 2021, we had another rollout for congestion pushback window with gains in reliability for low bandwidth networks. But it had lots of regression in quality. Early in 2022, we found the need for optimizing different networks by network types. So thus we wanted to formulate a solution based on ML. Here is the agenda for the talk. First, we will briefly introduce a couple of project topics for network characterization and network prediction. And then we will discuss in detail about challenges that we faced in developing these ML-based solutions. And then we will leave some takeaways and future plan for how we want to improve this project. Before we get into the details, let's look at the current bandwidth estimation algorithm. The current bandwidth estimation algorithm is based on Google's congestion controller. It is from WebRTC. It's a send-side bandwidth estimation algorithm. That means the bandwidth is estimated based on the feedback received from the receiver side. It consists of several modules like loss-based BWE, delay-based BWE, congestion pushback window. Here you could see multiple submodules and how they use the information from the receiver that it received. As you could see, these submodules have lots of parameters within them, and these parameters are tuned based on the network conditions. For example, in high bandwidth conditions, we want to ramp up really faster. Whereas in low bandwidth conditions, we want to ramp down really faster. So with these different network conditions, we have different parameters. And what we found with the existing approach is that it took lots of tuning on production. For example, we don't have good network scenarios for offline simulations. Thus, this resulted in multiple experiment iterations. And even after the experiment is done and rolled out, it is not clear if the optimal parameters are still applicable. For example, the users might have given up their old devices and moved on to new devices or new networks. It may not be applicable anymore, the optimization that we rolled out in the past. And also, as you could see, the system diagram itself was really complex. If you add more parameters to those, it has become a complex code logic for us to maintain, and it has lots of branches in them. Therefore, we wanted to formulate a solution based on ML. So ML gave us a cleaner alternative to untuned mules. But only point that we need to note down is we need to have a sufficient post-validation so that ML model doesn't give you results that is not reasonable. And also, ML models gave us a holistic approach to take network actions across multiple subsystems, such as bandwidth estimator, network resiliency, and transport. This gives us a good overall strategy for tackling different network conditions and what kind of optimization we want to do cross-stack. Next, I will hand off this talk to Leanne to talk in detail about network characterization, where she will talk about ML problem formulation, how we achieved good results for random packet loss.
Thanks, Santosh. Hello, everybody. My name is Li Yan. I'm ML lead in Meta. So since Santosh has talked about why ML-based is a better approach than hand-tuned rules, so I'll be talking about how we use ML-based approach to solve network characterization problems. So this slide defines what is a network characterization. So we have two endpoints. These two endpoints could be a desktop or a mobile device or with network devices. So in this example, we are showing a P2P connection. The offline tuned PWE optimal parameters are stored on the server side, while online inference is done on client side. So these slides talk about offline model learning and offline parameter tuning. So we leverage time series logs of network conditions in the past as the training samples. We use time series data because network signals are time varying and time sensitive. So the aggregated metrics cannot fully capture the full characteristic of the network and the dynamic of the network. These time series logs could be simulated network conditions or production logs. We also developed an internal tool called FB Learner workflow for model training using PyTorch. We also built up a client-side model deployment infer and inference pipeline on the client side. For offline tuning, we use simulation to run network profiles for the detected types, and then we will choose the optimal parameters for the modules based on matrix improvement. For the matrix, for example, we can use video quality or video freeze. So for the model architecture, since we are training on both time series data and non-time series data, we built a model architecture that could take input for both time series data and non-time series data. So for the time series data, we will pass through a LSTM layer, which is a long short-term memory layer that will convert the time series input into a vector representation. For the non-time series data, we will be directly passing through a fully connected layer. So then the two vectors will be concatenated together to fully represent the network conditions in the past. And then we will be passing through another fully connected layer. The final output from the neural network model will be the predicted output of the target variable. So in this slide, we will be talking about random packet loss classification and use this as an example of how we do network characterization. So the objective is that at current timestamp, if we see a packet loss, we want to characterize the current random packet loss as random or not based on the past n seconds network conditions. So for the model training, we will use time series data as input, and it will be passing through neural network layers like LSTM layer that we mentioned. And then we can get the vector representation of it. And then it will be passing through a classifier, and then the output will be the predicted probability of target variable. In this example, that will be the predicted probability of being a random packet loss. So we mainly use low-level features for BWE ML projects. So these low-level features can be collected at 100 milliseconds or 500 milliseconds or 1 second time intervals. And these can be collected during production calls. The features include packet loss rate, round-trip time with different evaluation types, and the jitter and the congestion window pushback. So these time series are usually collected in the past 10 to 30 seconds for our characterization work. So for this time series, we can also use feature engineering to extract and aggregate more powerful features to be directly used for the model. So this slide highlights different optimizations that we could use when the random packet loss is detected. For example, we will increase the tolerance to random packet loss in loss-based BWE. We can also ignore congestion signals in high bandwidth. We can also scale network resiliencies. So this part talks about network characterization. So next, Santosh will be talking about network prediction.
Thank you, Lian, for introducing the network characterization topic. Now let's go into network prediction. From Lian's introduction for network characterization, we know that network characterization only looks at the pass window for, say, for example, 30 seconds or 10 seconds to characterize networks into different types. One may ask, why do we need ML-based solution if we can characterize network based on simple untuned rules? One of the advantages of using ML-based solution is it can find out a dependency between multiple variables when we characterize networks. For example, it can find dependency between round trip time, that is RTT, packet loss, and then jitter. So during our execution, we found that it will be even more interesting and also very valuable for our product if we apply ML-based solution for network prediction. What we mean by network prediction is, given the past network conditions, can we predict the future network conditions? So that's what the rest of the talk about network prediction would be. So we felt the power of ML is further amplified if we use the ML-based solution for predicting future network conditions. Let's go deeper into a problem for predicting congestion. First, I will start with introducing the problem statement. Given the historical time series data from production or simulation for n seconds, the goal is to predict the packet loss due to congestion or the packet loss itself in the next n seconds. That is, a spike in RTT followed by a packet loss or a further growth in RTT. So this covers both shallow and deep buffers. That is, the shallow buffer causes packet loss when we incur congestion, and deep buffers cause increase in RTT when we incur congestion. Let's take a simulated example that we present below with the call dive. Here is a simulated network condition which alternates bandwidth every 30 seconds. It drops from high bandwidth like 500 kbps to 50 kbps every 30 seconds. As you could see, when the bandwidth drops, we see an increase in RTT right when it incurs congestion. And then it also sometimes incurs packet loss depending on the queue size. And we show our network prediction output in green that shows predicting the congestion well before the congestion happens based on our model training. The main challenge with congestion prediction is how do we go about labeling? The labeling is one of the important aspects of ML-based modeling. So either we could use ground truth from simulations or we could use ground truth from production. The challenge with using simulation is, can we get all the different types of network scenarios within simulation and what are the different distributions of congestion? So what we did is we used production for labeling our ground truth samples. So we have n seconds of time window in past and future. In our labeling, we use 4 seconds time window for past and future with the time series log, and we label congestion according to this big chart that we put up here. So to simplify this chart, we want to find out what are the positive and negative samples here. We look for RTT spike in the past and RTT growth in the future. Similarly, we look for packet loss in the past and packet loss in the future. To give you a simple example where we label positive examples, we look for RTT spike in the past, and if it results in the packet loss in the future, we strongly label this as positive example. And also, we look for RTT spike in the past, and if it results in further growth in RTT in the future, we label them as positive examples. So this is how we label the supervised model for predicting congestion using our ML approach. Once the model is trained, we evaluated the model on the test set using our performance metrics like F1 score, AUC, precision, and recall. We predicted congestion for 5.5% of our cases in our offline test using the congestion model. We also logged the ground truth for the model inference on the client side. What we did is, based on the past prediction, in the future window, we have the ground truth, whether the congestion has occurred or not. We log that ground truth from our ML inference on the client, and we compare that with the offline. So as we could see from this chart or the table here, the predicted congestion percentages for both offline and online evaluation are similar, and also we achieved a similar scores for AUC, precision, and recall. That tells you that the model is able to predict congestion closely as similar to the offline training. Once the congestion is predicted, we apply certain optimization similar to what Leanne mentioned for random packet loss. For example, in predicting congestion, we trigger more overuse. The overuse causes bandwidth to drop, so we are able to not congest more on the network. Similarly, we augment congestion signal to the existing congestion detector in the loss-based BWE module. And as I mentioned earlier in the talk, how do we do a holistic approach for bandwidth estimation and transport network resiliency? This is one example where we scale the network resiliency when we predict the congestion by sending more forward error packets. Finally, these are the results that we achieved by conducting our experiments on public clients. So our ML models are actually with BW optimizations are launched in both Messenger and WhatsApp. And the congestion prediction model yielded reliability wins. We saw a video freeze percentage increased by 2%. And similarly, for random packet loss, the model yielded quality gains of 3.4%, and the user engagement wins like talk time increased by 0.15%. So initially, if you remember from our talk, we wanted to address both reliability and quality gains by optimizing our ML-based solution for different network types. And that's what we achieved with this. Now I will hand off to Leanne to talk about conclusions and takeaways and finish this talk.
Thank you, Santosh, for talking about network predictions. So with that, I will be talking about conclusions and main takeaways from this talk. So from the explanation for network characterization and network prediction, we can see that ML-based approach is more efficient than traditional hand-tuned rules for network targeting, monitoring, and updating. We can also see that the efficiency of ML-based solution heavily relies on data quality and ground truth labeling. So if we can have a better data quality either from simulated data or production data, and if we can have a better ground truth labeling strategy, we can have better ML-based models. So ML's power is amplified by using it for model prediction problems, and it can also be automatically learning network actions. So currently, we are still exploring new areas for ML-based approach for network optimizations. So we have a few future plans, and currently we are exploring on these plans. So first, we are planning to develop and deploy more ML models for various applications. There is a need to design a generalized ML model for multitask architectures. We are trying to build a backbone model, which takes the network conditions in the past as the input and generate a representation of the network conditions. This network representation will be used to the downstream tasks for specific BWE optimizations and applications. And each downstream task will have its own target. So this generalized model architecture will greatly increase model scalability and reduce the model complexity for both offline and online. Secondly, so currently we are focusing on capturing network patterns within a short-term window from 10 seconds to 30 seconds. But it is also very important to capture long-term network patterns in the network. So our future plan also includes explorations of how to model long-term network patterns in the model prediction. Thirdly, we also plan to improve our simulation scenarios to build more realistic production-like network scenarios. We could even leverage GenAI to train generative models to generate more production-like network scenarios to reduce the gap between production and simulation. Last but not the least, our long-term goal is to use reinforcement learning to model BWE dynamically online instead of current strategy that we learn the ML model offline and then we apply the model online. So we will first work on how to come up with a good theoretical formulation of the model and a good reward function. And then we will apply our reinforcement learning onto our simulations-based network scenarios. Our ultimate long-term goal is to replace current network-based algorithm using reinforcement learning. So with that, we conclude our today's presentation, and thank you.
Hello, welcome to our last Q&A session. My name is Pavel Ponsky, and I'm an engineer on the video team at Meta. Together with me today are Sean, Mandeep, Tsahi, Lian, Santosh, and Ishan to answer your questions based on their last sessions that you have watched. So let's start with Tsahi. The question was, is it Google Meet that already switched screen share over to AV1 or someone else as a trial? What do we know about the usage of AV1?
So we don't know much. What we do know is that Cisco WebEx announced a year or two ago that they are starting to use AV1 for screen sharing on some devices, in some scenarios, but that was about it. What we see now in Google Meet is that they are starting to experiment with AV1 in different ways. What we believe is that we're going to see them use AV1 in low bit rates. During simulcast, or you'll be using VP8 or VP9 for the lower layers, but AV1 for the lowest bitrate, and in screen sharing. But it's not out yet. It's just things that you see and hints that we get from looking at the code and getting different bits and pieces of the SDPs from calls.
Thank you. Next question is to you, Mandeep. CPU and bandwidth restrictions were mentioned for the client in regard to logging and telemetry. How do you judge on the bandwidth, and how do you apply any throttling? Do you incorporate the bandwidth control for audio video?
Thanks. So I think the first thing I should point out is that the logging happens on a separate channel than the rest of the RTC communication, and we generally rely on the app infrastructure, so like Messenger or Instagram, like the standard infrastructure to do the uploading of logs. And there is some throttling implied, but we're very conscious about what we log, both for efficiency reasons and also for privacy concerns. So we're constantly working to make sure that we're only logging the data that we need. I think Ishan is a lot more versed in this topic on client-side logging. He might be able to add a few more details.
Yeah, totally. I can provide some details. So we do always want to make sure that logging does not compete in bandwidth with like audio and video. This is especially important for like users on like low bandwidth scenarios. So we do a lot of benchmarking to make sure that we are logging as minimal data as possible and as efficiently as possible. All of our components are modular as well. So we have like good communication between the media components and the logging components to make sure like bandwidth is utilized efficiently. And also that is one reason why a lot of our logging happens at the end of the call, so that like there is less chances of competition between the two.
Thank you. Great answer. Now, Sean, question to you. How do you compare Python to something like Janus and MediaSoup? Other than use of Go as programming language, is there any intrinsic benefit to using Python for building the WebRTC backend?
I tend not to compare different implementations head to head. Like what my attitude on this is that depending on who you are, like you should use what works best for you. So if you have like a code, imagine if you have like all your code is already in JavaScript, it'd probably make more sense to use Janus. Or if like you feel really comfortable with like a config driven and you have some things like Janus RTP forwarders could be perfect if like you have that exact use case. So I've contributed to libdata channel, MediaSoup and Janus, and I think they all have like particular strengths. But the reasons that I care about Python or why I continue working on it is like, for me, it's an API, not a server. So like with Python, you can build SFUs, you can build media servers, but it's also used in a lot of like popular security cameras. People put Go on the cameras now, peer-to-peer networks and VPNs. So my attitude, or like what I've seen, is the fact that since Python has such a wide user base, that it's made the code base better, more resilient, and covers more things. And then leading into like, is the only reason to use Python is because of Go? Like that is a big part of it. Like Go is a fantastic programming language. Like it's built for teams. Like the fact that I have a package manager built in, the fact that it's really simple. Like I love that new grads can come on and start contributing to Python. Like that's really, and I think that same goes for like people building with Python, that you can be starting out your company and know nothing about RTC and not be, a C++ wizard, but you can go and pull Python off. And then the last part that Python, that I think that makes it effective for people, is it's more than just code. Like the Python code base is split out. So, like ICE is in its own repo and DTLS and RTCP. And the truth is, like, when you run it, you can go use a managed WebRTC service, but when you run into a problem, you're going to have to talk the language. Like, you're going to have to debug things. And it's not enough to just show up and say, like, oh, there's no video on the screen. And for me, like, that's why I do things like WebRTC for the curious, and I do these, and I don't have like a big mono repos, because I want people to understand and know how to use things. So yeah, that's like, I break it. Those are like the three things that today keep me going, is like, I think it's great as an API. I think it's like Go as a language is great. And Python for me is becoming more and more about like the education of WebRTC and not just like a blob of software.
Great answer. Thank you, Sean. And you all know you can reach out to Sean on a Slack channel. Not okay. Next question, Santosh. What are the main challenges in building a simulator for RTC?
Yeah, thank you for the question. One of the biggest challenges that we faced is how to convert the production traces into like network profiles for simulations. For example, a production
will have lots of different network types. So one thing that we did is like we have heuristics built on top of the production traces to convert them to network profiles. And we are experimenting with that for training our ML models. And also, our existing simulation tools are built on top of WebRTC's performance tests. There's nothing more big about building the simulation. It's a simulation tool itself, but more about production traces. How do you convert into network profiles?
Thank you. Fantastic answer. Next question is to you, Tsahi. So, a very serious question. How many balls can you juggle at the same time?
Well, I knew this was coming, so this is my maximum, 4. I do 3 clubs. I juggle twice torches. And I also juggle a single kettlebell, which is this huge weight.
But with all the seriousness, with so many changes in WebRTC, how should a developer keep up with the changes and the skills in this domain, especially for maybe for new developers that coming up to this area?
So I guess it's really hard. It starts with the fact that WebRTC is multidisciplinary to begin with. You need to know a bit about signaling and networking and browsers and voice over IP and how media is sent over the network and how codecs work and devices and peripherals and servers. So there is a lot to it. There is a WebRTC for the curious. It's an online book. Then there are my courses, the WebRTCcourse.com. There is WebRTC Insight Service. There is Discuss WebRTC, where you can ask questions. WebRTC Hacks for the technical stuff when you actually go into deep diving into stuff. So I guess it's not a good answer because there's so much to go and look and see and be on top of. So you need to figure out your way in there. And also as a developer, what it is that you're most passionate about. Is it the optimization piece of it? Is it the codecs, the quality part, the monitoring and the logging part, the UI, and the fluidity of it? Once you pick that route, it's easier to go and dig deeper into that specific domain.
Thank you. Next question is to Mandeep and Ishan. So it seems like what Rator doing is a stream processing. Have you considered using an off-the-shelf stream processing framework like Apache Flink? I think it's very relevant to people who are listening and watching this series today.
Yeah, so great question. I'm not familiar with that particular open source solution, but we have looked into our internal stream processing solutions at Meta. And generally, actually, the very first implementation before my time of Ralligator was actually built on one of these stream processing solutions. And there were a few challenges it ran into. And one of them being there was limited support for working with multiple streams and processing multiple streams at the same time. And 2, just our scale, it couldn't handle. And the main reason was the way we actually run our completion logic. It runs on a timer, and most stream processing frameworks don't have support for something like that. So you usually have all the data coming in, and even if you support multiple streams, you have to meet some condition when events arrive on one of those streams, and then write your output. Here we want to periodically run our output loop because we have timeouts. Sometimes some of the data that we're waiting on is never going to arrive. So that's one of the main reasons. Those are some of the main reasons.
Thank you. Lian, next question is for you. So machine learning-based bandwidth prediction, how big is the model compared to existing GCC? For reinforcement learning technique in the future plans, will it be done in deployment or in a production network that emulates typical deployment scenarios? What are your thoughts about it?
Thank you. That's a great question. So our model size depends on our model structure and the model complexity. So currently, our model size varies from like 20 KB to even 100 KB. That depends on our model complexity. So for the deployed model that we have currently, like congestion model and packet loss model, the model size is around 30 KB. So it's quite a small size model on device. And for the reinforcement learning technique in the future plan, we will test and iterate on simulated networks first. But our ultimate goal is to launch and deploy in the production environment. Thank you.
Thank you, Lian. Great answer. Sean, the next question is to you. What is your thought on running a company with fully open source product and trade-off between open source governance and philosophy and for-profit needs?
It's hard. It's definitely, and it's something that's new to me. I've only been doing this for 6 months. So for me with Pion, I always worked on things that like either I thought were deeply important to the quality of the project or were deeply important to the users of the project. And that's a pretty easy thing to do. Like I'm not being pulled in many different directions. And with LiveKit, now I have, users that are coming in from the open source side that, they're telling me things that are important. But the truth is that if you use LiveKit and you're not paying for it, that I can't keep working on LiveKit if you're not a paying customer yet. So like it's a very different reality. And so, yeah, like there are these things that you have to work on. But I've had this conversation with a lot of people, and one that really rang out with me, like, as I was talking to Colleen, and she was telling me, like, as long as you line up your incentives with your users, in the end, like, you will feel good about what you're doing and you will have good results. And so I'm trying really hard to do that. Like, there's no like simple, follow these 12 steps and you can have a great open source company. But I think I make sure, like, when I go and talk to customers, that I always recommend like what I believe is best for them. That when I go and build things, I'm trying to build things for like the long-term quality of the product, that I have to support growing LiveKit, but at the same, yeah. So I don't know. I could talk about this for hours, and there's all these like different things and points. But yeah, it's not easy, and like so many people struggle with it and talk about it, and I'm trying my best, and I'm happy to talk. I succeed the rest of my time because I could keep going. But yeah, that's where I'm at today. This is new to me and it's challenging, but we're trying our best.
I can feel pain as an open source project maintainer, not the same scale, but it's definitely takes a lot of work. Next question, Santosh, is for you. Is it possible to run ML-based bandwidth estimation congestion control on top of GCC in the browser? Is there any plan for that?
Thanks for the question. The currently developed models, we are running only on native apps, especially like mobile devices. We don't have immediate plan for running on browser, but the solution that we have developed so far is applicable for browsers. For example, you can run an ML model, and if you are able to intercept network signals, for example, RTT, packet loss, jitter, as we mentioned in our talk, we should be able to like characterize network into different types and apply optimization. For example, WebRTC is mostly controlled to the field trial configurations, and if you can control that based on the network type, that's something is possible potentially for web browsers. Other than that, actually replacing the GCC module, we need to like work closely with the upstream WebRTC to change it for using ML-based approach.
Thank you. Thank you for the answer. Mandeep and Ishan, the next question is for you. You mentioned that the distributed key value store management is very expensive. Can you please elaborate on why is it so expensive?
So generally because there's replication involved. So you have to, there's the current internal key value store that we have, it does 5x replication. So that's 5x the data storage cost, and the data storage technology they use is usually flash or something expensive of that nature. And we necessarily don't need that type of latency for our use cases. And then again, you have to send all of that data over the wire, and then read it back once you've collected, aggregated all the logs to process them and write out the aggregated results for our data pipelines. So mainly that sort of, amplification of the writes and then the reads is what makes it expensive. And the distributed sort of event processing system like Scribe that we have, it's already doing the replication, and so it has the data there if we wanted to reprocess it. So it generally would mostly be wasteful to use a well implemented key value distributed key value store. Yeah, thank you.
Thank you for your answer. Santosh, a question to you. So I think it's a very generic question. It's very interesting. What's the biggest challenge you faced in training networking machine learning models for RTC? And I think that could be probably expanded to not only networking.
Cool. Thank you for this question. I was hoping someone would ask this question. The biggest problem that we faced is ground truth labeling, especially for devising a solution for BWE, where the ground truth is not present. Initially, we leverage simulation to train the model. What we noticed with using simulation for training the model is it doesn't generalize well for production networks. And since we wanted to see if we could move to like directly using production data for labeling, but the problem there is the data could be like wide varying characteristics. And we even tried unsupervised training for some of the classification tasks. With unsupervised, you don't need labels. Rather, you use clustering like algorithms to classify networks into like good bandwidth and bad bandwidth networks. But overall, we strongly believe that the performance of ML-based solution especially for bandwidth estimation depends on the ground truth. We are taking a careful approach here. We are trying to build a better production scenario, as we mentioned in the start of this question and session, for our simulations. With that, we should be able to have a good production-like networks imitated on simulations where we train the model. Thank you.
Thank you for a great answer. And this is going to be our last question. So, Tsahi, what is the area that fascinates you the most with WebRTC these days?
I think it's mostly where exactly we're going. On one hand, you see all of the industry and the vendors going towards machine learning and unbundling of WebRTC and how do you do stuff in a way that differentiates us from others on top of this open source thing called WebRTC inside the browsers that limit what we can do. So that's one thing. While at the same time, there's let's try something new, not WebRTC. Let's use web transport with web codec and WebAssembly and see what we can get from that. How can we push the envelope there? And what use cases can we take away from WebRTC and do it in a different way? Again, for the purpose of differentiation. And then there is the new work around media over quick, like a brand new protocol that is going to be there to do things totally differently or the same, just under a different name. So where we're going to be in a few years now versus today is going to look very differently. And I just can't wait to see how would that develop, what will get us there.
Thank you. That's a great answer. So I actually have time for a few more questions. Ishan, the question is for you. Do you use observability metrics in real time and change call quality in real time? If you can give an example, if possible.
Yeah, that's a really good question. So as we mentioned in like the future scope of our talk, this is not something that we do currently, but this is something that systems like Rallygator can make us possible. We can like stream logs continuously, and then we can monitor them and like debug real-time calls, and we can change configuration on the fly for adjusting things like call quality. So we definitely hope that in the coming years, we'll be able to do this effectively and get a lot of value out of it. And there is even the possibility of using even more advanced techniques like machine learning, which could do this automatically after analyzing the calls. So I really look forward to the future scope in this area.
Thank you, Sean. And now really to the last question. Santosh and Liana, this question is for you, machine. Have you tried applying machine learning solutions for other networking problems beyond bandwidth estimation?
Yeah, I can answer this question. We tried for optimizing network resiliency by detecting packet loss. Other than that, most of the time we have spent on bandwidth estimation and improving the bandwidth estimation. One approach which is in development is generalized network characterization, where we categorize network into multiple types, and it's a multitask learning approach that we are developing within our networking org. The idea there is to once you have multiple signals from the generalized network characterization, can we do a holistic optimization across multiple modules, for example, bandwidth estimator, network resiliency, and transport. That is in development, and we look forward to launching it in production in the near future. Thank you.
Thank you. And that's a wrap. Thank you for joining us and the audience question that you submitted. Thank you all.
As we close today's event, I want to thank everyone for an engaging day. We covered a lot today, including opportunities, challenges, and exciting growth areas that we will likely hear more about in future events. The high engagement from the RTC community is what makes events like this possible and so rewarding. We are looking forward to exciting developments in this space that will fuel our discussions in the coming year. If you are interested in sharing your work or ideas at our next RTC event or any AtScale event, please head to the speaker submissions page on the AtScale conference website. Your participation is what makes these discussions so rich. As we conclude today's program, I would like to thank each one of you for your active participation. Your insightful questions enriched our discussions and also highlighted the dynamic spirit of the RTC community. A special note of appreciation goes out to all our speakers. Your invaluable contributions have been the base of today's achievements. All the content from today will be available on the AtScale website and social media pages soon. There's still time to sign up for an email notification when the content is live by registering for this event if you haven't already. Looking ahead, don't forget to mark your calendars for Data at Scale in May and System at Scale in June. I'm also excited to share that System at Scale will be our first hybrid event since the pandemic, offering both in-person here at Meta's Menlo Park office and virtual participation options. Registration is open for both of these events, and I encourage you to subscribe to the AtScale mailing list for all the latest updates. Thank you all again for joining. We hope you enjoyed the program, and I really hope to see you again next year.